countless millennia, humanity gazed into the night sky, their understanding limited to the naked eye, the flickering flames of distant campfires, or the gentle glow of oil lamps. They saw a celestial tapestry, seemingly fixed and eternal, a grand dome adorned with countless stars, their patterns familiar, their positions unchanging over generations. The universe was, in their minds, a static, unchanging backdrop to human drama, a stage upon which life unfolded. Philosophers and early astronomers, from Aristotle to Tycho Brahe, largely reinforced this view, though their methods grew increasingly sophisticated. They meticulously mapped constellations, predicted planetary movements with astonishing accuracy given their tools, and developed complex models of a geocentric, or later, a heliocentric, but always, fundamentally, a bounded and stable cosmos. This perception of an unmoving, immutable universe permeated art, philosophy, and religion, shaping our collective consciousness and placing humanity at the center of a seemingly unchanging realm. It was a comforting thought, a universe that, despite its vastness, felt intimately known and constant. Yet, the seeds of a radical shift in this profound understanding were already being sown, quietly, in the minds of a few intrepid thinkers who dared to question the obvious. Then came the dawn of modern astrophysics, heralded by the invention of the telescope. Galileo Galilei, with his crude yet revolutionary instruments, turned his gaze skyward and shattered centuries of dogma. He revealed mountains on the moon, phases of Venus, and moons orbiting Jupiter, proving definitively that not everything orbited Earth. His observations, radical for their time, began to chip away at the geocentric static model, though the concept of a static universe persisted in a larger sense. Newton's laws of gravity, while explaining celestial mechanics with unprecedented precision, also implied an inherent instability for a finite, static universe. It should collapse under its own gravity. To reconcile this, Newton himself famously proposed an infinite universe, uniformly distributed, where gravitational forces would average out. Even Albert Einstein, in his groundbreaking theory of general relativity, initially introduced a cosmological constant, a repulsive force, specifically to maintain a static, non-collapsing universe, demonstrating just how deeply ingrained the static paradigm was, even for the most revolutionary minds of the 20th century. This constant, a fudge factor in his own words, was a testament to the prevailing belief that the universe, on its grandest scale, must remain unchanging, timeless, and eternally poised. The scientific community, though now embracing a much larger, more dynamic cosmos, still clung to the idea of its fundamental stillness. The true unraveling of the static universe began with the perplexing phenomenon of redshift. In the early 20th century, astronomers, using increasingly powerful spectroscopes, noticed something peculiar about the light arriving from distant galaxies. Instead of emitting light at exactly the same wavelengths as observed in labs on Earth, the spectral lines of these galaxies were systematically shifted towards the red end of the electromagnetic spectrum. Christian Doppler had already explained a similar effect for sound waves. The pitch of an ambulance siren changes as it moves towards or away from you. For light, this meant that objects moving away from an observer would appear redder, while objects moving towards them would appear bluer. Initially, these observations were perplexing. Vesto-Slipher, meticulously observing spiral nebulae, found that most of them were indeed moving away from the Milky Way. This wasn't just a handful of exceptions. It was a consistent pattern, revealing a universal recession. The redshift wasn't random. It possessed a distinct proportionality, hinting at a hidden order within the cosmic dance. It was almost as if the universe itself was engaged in a grand outward ballet, with every distant galaxy performing a slow retreat from our vantage point, beckoning scientists to understand the underlying mechanics of this cosmic waltz. Then came Edwin Hubble, the visionary astronomer who, arguably more than anyone else, reshaped our cosmic perspective. Working at the Mount Wilson Observatory in the 1920s, Hubble made two groundbreaking discoveries facilitated by the powerful 100-inch Hooker telescope. Firstly, he conclusively proved that many of the faint nebulae previously thought to be gas clouds within our own galaxy were, in fact, independent galaxies far beyond the Milky Way's confines. This instantly expanded the perceived size of the universe from a single galaxy to an unimaginable multitude of island universes. Secondly, and even more profoundly, by combining his distance measurements of these galaxies with Vesto-Slipher's redshift data, Hubble meticulously charted a definitive relationship. The farther away a galaxy was, the faster it appeared to be receding from us. This became known as Hubble's law. It presented a startling conclusion. The universe was not static. It was unequivocally expanding. This was not merely abstract theory. It was direct, observational evidence, meticulously gathered and rigorously analyzed, painting a dynamic new picture of reality itself, forcing us to reconsider everything we thought we knew about the very fabric of existence on the grandest scale imaginable. The revelation of an expanding universe naturally led to a monumental question. What was expanding from? The logical inference pointed to a singular beginning, a moment when all the matter and energy in the universe were compressed into an extraordinarily dense and hot state. Georges Lemaitre, a Belgian priest and physicist, was among the first to propose this radical idea in the late 1920s, referring to it as the, quote, hypothesis of the primeval atom. He suggested that the expansion we observe today is simply the ongoing aftermath of this singular event. This concept, later somewhat derisively nicknamed the Big Bang by astronomer Fred Hoyle, despite his preference for a steady-state model, gradually gained traction. It wasn't just a theory. It was a narrative that elegantly wove together the mysterious redshift with a scientifically plausible origin story for the cosmos. This new understanding transformed our cosmic narrative from one of eternal stasis to a dynamic, evolving epic, where time itself had a genesis, and the universe was born from a cataclysmic singularity, setting in motion the grand cosmic dance we observe today, leading inevitably to an ever-expanding, cooling, and evolving dominion of stars and galaxies. The Big Bang theory received its most significant boost in 1964 with the accidental discovery of the cosmic microwave background radiation, or CMB. Arno Penzias and Robert Wilson, engineers at Bell Labs, were attempting to detect signals for satellite communications using a large horn antenna. No matter where they pointed their antenna, they detected a persistent, uniform hiss, an unexplained static that seemed to come from all directions in space. They meticulously checked their equipment, even removing pigeon droppings from the antenna, but the noise persisted. Unbeknownst to them, across the country, a team of theoretical physicists at Princeton, led by Robert Dicke, was actively searching for exactly this phenomenon. Their calculations predicted that if the universe began with a hot Big Bang, there should be a faint, uniform afterglow of radiation detectable today, redshifted down to microwave frequencies. The noise Penzias and Wilson were detecting was precisely this relic radiation, the fossilized light from the universe's infancy, cooled and stretched over billions of years. This serendipitous discovery was a profound validation, providing a direct observational link to the early, hot universe, effectively cementing the Big Bang as the leading cosmological model. It was, quite literally, the sound of creation, echoing through the vastness of space. With the CMB as compelling evidence, cosmological research exploded. The Big Bang theory, now a robust framework, was refined and expanded to include concepts like cosmic inflation, a fleeting period of extremely rapid exponential expansion in the universe's first sliver of a second, proposed to explain its remarkable uniformity and flatness. Further observations, such as the abundance of light elements like hydrogen, helium, and lithium in the universe, were found to be in exquisite agreement with predictions made by Big Bang nucleosynthesis, the theory describing the formation of these elements in the first few minutes after the Big Bang. The large-scale structure of the universe, the grand cosmic web of galaxies and clusters separated by vast voids, also perfectly aligned with simulations based on an expanding universe where initial quantum fluctuations grew into the structures we observe. These interconnected pieces of evidence formed a powerful, seemingly unassailable edifice of understanding, a testament to humanity's ability to decipher the deepest secrets of reality. The universe, we concluded, was not just expanding. Its entire history, from birth to present, was a dynamic, evolving saga, meticulously detailed and understood. For decades, the expanding universe model became foundational to astrophysics. Generations of scientists were educated under its tenets, its calculations filling textbooks, and its implications shaping philosophical thought. We built bigger telescopes, launched space probes, and designed more complex simulations, all aimed at dissecting the nuances of an expanding cosmos. From measuring the precise rate of expansion, known as the Hubble constant, to understanding the accelerating expansion driven by enigmatic dark energy, our scientific endeavors were deeply rooted in this paradigm. It provided a coherent narrative for everything from the origins of stars and galaxies to the very future of the universe, whether it would expand forever, eventually cool to absolute zero, or perhaps ultimately collapse back in on itself in a big crunch. The intellectual landscape was dominated by this grand conceptual framework, a testament to scientific progress and humanity's seemingly unyielding march towards complete cosmic understanding. The very word universe became synonymous with expansion, a dynamic entity forever moving, evolving, and stretching towards an unknown destiny, its origins etched into the very fabric of space-time itself. Despite its overwhelming success, a few subtle cracks occasionally appeared in the otherwise robust edifice of the Big Bang model. Like faint whispers in the grand cosmic symphony, some observations seemed to deviate from the expected harmony. The Hubble tension, for instance, emerged as a vexing discrepancy. Different methods of measuring the universe's expansion rate yielded slightly different, yet statistically significant values. One method, using the cosmic microwave background, gave one rate, while another, relying on observations of distant supernovae, yielded a persistently higher one. This wasn't a minor rounding error, it was a puzzle that hinted at either unknown physics or a fundamental miscalculation. There were also anomalies in the distribution of galaxies on the largest scales, or the unexpected alignment of certain quasar groups that seemed to defy the cosmological principle. The idea that the universe is homogeneous and isotropic on large scales, while these concerns were often dismissed as observational errors or statistical flukes, or perhaps minor adjustments to an otherwise sound theory, they lingered in the minds of a few independent thinkers. These were the quiet dissonances, the faint echoes of an alternative truth waiting to be discovered, patiently challenging the established order from the periphery of mainstream thought, urging a deeper, more fundamental reevaluation of reality itself. Enter Dr. Aris Thorne. A reclusive, brilliant theoretical astrophysicist, Thorne had spent the better part of his career on the fringes of mainstream cosmology, not because he was an outcast, but because his mind instinctively sought out the edges of accepted knowledge, the places where current theories faltered or ran into logical impasses. While colleagues diligently worked to refine the existing Big Bang model, Thorne found himself increasingly drawn to the subtle discrepancies, the elegant solutions that seemed to demand an inelegant explanation, the very fudge factors that kept the accepted model afloat. He was a meticulous researcher, driven not by a desire for fame, but by a profound intellectual curiosity and an almost obsessive need to understand the universe at its most fundamental level. He saw beauty in simplicity and often felt that the expanding universe model, while functional, was becoming overly complex, requiring too many adjustable parameters to fit every new observation. It wasn't enough for a theory to merely work. Thorne believed it must also possess an inherent elegance, a predictive power that didn't rely on constant adjustments. His quiet studies, conducted in the solitude of his home office, littered with notes and arcane texts, were about to ignite a firestorm of controversy. Thorne's journey began with a deep dive into the very foundation of the expansion theory, redshift. He understood its accepted explanation, the Doppler effect applied to light, where galaxies moving away from us cause their emitted light waves to stretch, shifting towards the red end of the spectrum. But he questioned the inherent assumption that this was the only possible mechanism for redshift on cosmic scales. What if there was another, more subtle interaction, a fundamental property of space itself, that could cause photons to lose energy and effectively redshift as they traversed vast cosmic distances? This wasn't the old tired light hypothesis, which merely suggested photons lost energy randomly over time, a theory largely dismissed because it incorrectly predicted image blurring. Thorne envisioned something far more sophisticated, a systematic, predictable, and measurable interaction with the very fabric of spacetime, hinting at a hidden layer of cosmic physics that had been entirely overlooked by generations of scientists. He began to meticulously review historical redshift data, searching for patterns, anomalies, or subtle deviations that might offer a clue to this elusive, alternative mechanism, a glimmer of truth hidden in plain sight. Thorne theorized that the common understanding of space as a passive, empty void might be fundamentally flawed. Instead, he proposed that space, even in its vacuum state, was imbued with a subtle, dynamic energy field, a kind of ultrafine cosmic ether far more complex than anything previously conceived. He posited that photons, as they traveled across billions of light years, didn't just glide through this void, they subtly interacted with it, exchanging infinitesimal amounts of energy with this underlying cosmic fabric. This interaction wasn't random or lossy in a simple sense. It was a cumulative effect, a gradual stretching of the photon's wavelength, a sort of quantum friction caused by the photon resonating with or traversing through a medium that possessed a non-uniform impedance over cosmic scales. Imagine a wave passing through a medium that very subtly changes its properties over vast distances. The wave's characteristics would be altered, its wavelength lengthened, giving the precise appearance of a Doppler redshift, without any actual motion of the source. This visionary concept departed significantly from established physics, suggesting an entirely new interpretation of the fundamental interactions between light and space. Thorne named his nascent hypothesis Cosmic Fabric Interaction Theory, or CFIT. It was a bold departure from both the expanding universe model and older, discredited, tired light theories. CFIT wasn't about photons losing energy through random collisions or simple degradation. Instead, it proposed a fundamental, predictable interaction with the very quantum structure of space-time itself. He suggested that space-time wasn't merely a backdrop, but an active participant in the propagation of light, imbued with inherent energetic fluctuations that cumulatively altered the wavelength of traversing photons. This subtle interaction, consistent over vast distances, would produce a redshift precisely proportional to distance, perfectly mimicking the observed Hubble's law. Imagine a photon, like a tiny wave, encountering a resistive medium in space itself, causing it to stretch slightly with every billion of light years it travels. The accumulated effect, over cosmic distances, would precisely account for the redshift we observe, without needing to invoke any universal expansion. This was a paradigm shift, proposing a universe fundamentally quiescent, yet deceptively dynamic in its optical manifestations. One of the immediate challenges for CFIT was explaining the cosmic microwave background. If the universe wasn't born in a hot Big Bang, how could there be a uniform, pervasive microwave glow? Thorne proposed that the CMB wasn't an afterglow of creation, but rather an intrinsic property of the static universe itself. He theorized that the cosmic fabric he posited wasn't perfectly cold and empty. Instead, it possessed a fundamental, irreducible background energy, a cosmic hum, perhaps a manifestation of its quantum fluctuations or a radiative equilibrium established over an infinite past. This background energy, when distributed across the entire static cosmos, would naturally settle into a blackbody spectrum corresponding to roughly 2.7 Kelvin, precisely matching the observed CMB. In this view, the CMB was not a relic of a past event, but a constant, inherent thermal bath of the universe, suggesting an eternal, self-sustaining cosmos rather than one with a definite beginning. This radical reinterpretation of the CMB, if proven, would not only dismantle the Big Bang's strongest pillar, but also usher in an entirely new philosophy of existence, suggesting a universe without a temporal genesis, a timeless entity existing in perpetual equilibrium. Next, Thorne turned his attention to the observed abundance of light elements: hydrogen, helium, and lithium. The Big Bang model perfectly predicts their cosmic ratios, as they were supposedly forged in the universe's initial fiery moments. This was a strong point for the Standard Model. However, Thorne countered that while the Big Bang offered one explanation, it wasn't necessarily the only one. In a static universe, he argued, these elements could still be formed and maintained through a continuous, long-term process of stellar nucleosynthesis and supernovae, recycling matter over eons. Furthermore, unseen mechanisms or properties of his cosmic fabric could potentially influence elemental abundances over vastly extended timescales, perhaps even facilitating new forms of atomic interactions not yet understood. While acknowledging that this aspect of CFIT was less developed, he stressed that a static universe didn't preclude the existence of these elements, merely their origin solely from a primordial Big Bang. His argument was that correlation does not always imply direct causation. If the Big Bang model fit the elemental abundance, it didn't automatically invalidate all other possibilities, especially if a static universe offered a more elegant explanation for other phenomena. Thorne published his initial papers quietly, primarily in theoretical journals, knowing the radical nature of his ideas. He wasn't seeking immediate confrontation, but rather intellectual discourse among peers. His propositions were met with a predictable mix of skepticism and polite dismissal. Many simply reiterated the established evidence for the Big Bang, finding Thorne's cosmic fabric interaction theory an unnecessary complication, an attempt to solve problems that mainstream cosmology considered already settled or minor anomalies. Some critics argued that his theory lacked a concrete, testable mechanism for how photons would interact with this cosmic fabric in such a precise, cumulative way, without violating established physics principles like energy conservation or Lorentz invariance. They demanded rigorous mathematical derivations and empirical predictions that directly contradicted the Big Bang, not just offered alternatives. It was a lonely path, but Thorne was undeterred. He believed that the true test of a theory lay not in its immediate acceptance, but in its ability to withstand scrutiny and offer novel, testable predictions. He knew that to truly challenge a century of accepted wisdom, he needed more than just a plausible alternative. He needed incontrovertible evidence, something that pointed directly to a static universe and unequivocally refuted the expansion. The scientific community, though outwardly dismissive, wasn't entirely oblivious to Thorne's work. His radical interpretations, though unconventional, occasionally sparked hushed debates in faculty lounges and at obscure workshops. Young, aspiring researchers, unburdened by decades of preconceived notions, found a certain allure in his bold challenge to the status quo. Some recognized the elegance of his theory, even if they doubted its feasibility. A few maverick physicists who themselves harbored quiet doubts about certain aspects of the Big Bang reached out to Thorne, offering to collaborate or provide data. This was the nascent underground, a network of curious minds willing to entertain ideas outside the mainstream. Thorne, always eager for intellectual exchange, began to forge quiet alliances, pooling resources and expertise. This collective curiosity, albeit initially marginalized, slowly began to foster a powerful, albeit subtle, momentum. It was in these hidden discussions, these clandestine collaborations, that the seeds of a revolution were truly sown. Far from the public glare and away from the entrenched dogma of established institutions, critical to Thorne's strategy was revisiting the cosmic distance ladder. This intricate sequence of methods allows astronomers to measure distances to progressively more distant objects. It starts with parallax for nearby stars, then uses standard candles like Cepheid variable stars for intermediate distances, and finally relies on type Ia supernovae for the farthest reaches of the universe. Each rung of this ladder builds upon the previous one, meaning any fundamental error in the lower rungs cascades throughout the entire cosmic distance scale. Thorne hypothesized that the very concept of standard candles might be subtly misinterpreted in an expanding universe. He speculated that if his cosmic fabric interaction theory were true, the apparent brightness of distant standard candles might not only be affected by distance and redshift, but also by the cumulative interaction of their light with the cosmic fabric itself, leading to a miscalibration of their intrinsic luminosity over vast cosmic distances. This subtle effect, if unaccounted for, could explain the observed dimming of distant supernovae without invoking dark energy or an accelerating expansion. It implied that the universe wasn't expanding faster and faster, it was simply being observed through a slightly different lens due to the inherent properties of space. The accelerating expansion of the universe, discovered in the late 1990s and attributed to dark energy, was another major piece of evidence Thorne set out to reevaluate. Observational data from distant type Ia supernovae showed that they were dimmer than expected for a uniformly expanding universe, suggesting that the expansion was speeding up. This led to the inference of a mysterious, repulsive force permeating space, driving this acceleration. For many, this was the ultimate triumph of the Big Bang, albeit with an enigmatic new component. However, Thorne saw this differently. He argued that if his CFIT was correct, if light progressively lost energy and redshifted due to interactions with the cosmic fabric, then distant supernovae would naturally appear dimmer. Their light would be stretched and diluted not by an accelerating expansion of space, but by the cumulative effects of traversing a static, interacting medium. This offered a far more parsimonious explanation, eliminating the need for an unknown, all-pervasive dark energy, which accounts for over 2/3 of the universe's energy density. It was a bold claim, directly challenging the Nobel Prize-winning discovery and implying that one of the most significant cosmological discoveries of the past few decades might have been a profound misinterpretation of optical phenomena in space itself. Thorne knew that reinterpreting existing data was only the first step. To truly challenge the established paradigm, he needed robust, novel predictions that could be specifically tested. He meticulously refined the mathematical framework of CFIT, working tirelessly to quantify the precise interaction between photons and his proposed cosmic fabric. His calculations suggested that if the universe was truly static, there should be subtle, measurable differences in how angular sizes of distant galaxies appeared. In an expanding universe, galaxies at a certain redshift should appear larger than they would in a static universe due to the expansion-stretching light paths. Thorne's theory predicted a slightly different angular size relationship, a minute divergence from the Big Bang's predictions that might only be detectable with extremely precise astronomical observations using the next generation of telescopes. This was his critical test, his smoking gun, a clear, quantifiable difference between his static universe model and the prevailing expansion theory. It was a daunting challenge, requiring technological capabilities that barely existed, but it was a path to potentially revolutionizing our entire understanding of the cosmos, a journey into the deepest mysteries of space and time. Thorne presented his refined CFIT model at a small, specialized astrophysics conference, choosing a niche forum over a grand stage. He opted for a detailed technical presentation, complete with complex equations and intricate simulations, rather than a broad, sweeping declaration. His arguments were methodical, his tone measured, devoid of dramatic pronouncements. He began by systematically dismantling several perceived proofs of expansion, meticulously detailing how CFIT could offer an alternative explanation for each one, from the redshift to the CMB, and particularly focusing on the Hubble tension and the supernova dimming anomaly. He articulated the subtle angular size predictions, emphasizing their testability. The audience, a mix of established professors and curious young researchers, listened with a blend of professional skepticism and cautious intrigue. Some scoffed, others asked challenging, probing questions, but a few, sensing the potential for a genuine paradigm shift, leaned forward, taking copious notes. The air in the lecture hall crackled with intellectual tension, a quiet storm brewing beneath the surface of polite academic discourse. It was a moment of subtle defiance, a single voice courageously challenging a choir of long-held beliefs, sowing seeds of doubt where certainty once reigned. Among those captivated by Thorne's presentation was Dr. Elena Petrova, a brilliant observational astronomer with a reputation for meticulous data analysis and an unwavering commitment to empirical truth. Unlike many of her peers, Elena possessed an innate skepticism towards unchecked consensus and an intuition for identifying subtle numerical irregularities. She had for years been quietly troubled by the Hubble tension, seeing it not as a minor nuisance, but as a stark indicator of a deeper, perhaps undiscovered cosmological flaw. When Thorne articulated how CFIT could provide a coherent explanation for this very tension, she felt a profound resonance. His theory offered a more elegant resolution than simply adding new, hypothetical components to the standard model. After the session, she approached Thorne not with immediate acceptance, but with a barrage of incisive questions, pushing him to clarify the practical implications and testable predictions of his theory. Their conversation stretched late into the night, a meeting of two formidable minds, each recognizing in the other a shared dedication to uncovering the universe's true nature, regardless of how unsettling the revelations might be. This was the beginning of an unlikely but powerful collaboration, poised to shake the very foundations of cosmology. Petrova, along with her research team, began sifting through enormous data sets from previous cosmological surveys. Their initial focus was on the angular size measurements of distant galaxies. If the Big Bang theory was absolutely correct, there was a specific, well-defined relationship between a galaxy's observed angular size and its redshift. However, if Thorne's CFIT was true, predicting a static universe where light interacted with the cosmic fabric, then the angular sizes of these same galaxies should deviate slightly from the Big Bang predictions, particularly at very high redshifts. It was an incredibly subtle effect, requiring immense precision and the statistical power of observing thousands, even millions of galaxies. They were looking for a needle in a cosmic haystack, hidden within layers of noise and observational biases. The work was painstaking, involving countless hours of data processing, sophisticated statistical analysis, and rigorous error checking. It was a race against intellectual inertia, a quiet challenge to decades of established wisdom, conducted in the hushed glow of computer screens, where every pixel, every photon, held a potential key to unlocking the universe's true, hidden nature. As months turned into a year, Petrova's team began to see preliminary patterns emerging from the angular-size data. They weren't immediately conclusive, but there was a consistent, albeit slight, deviation from the Big Bang predictions, particularly at the highest redshifts, precisely where Thorne's CFIT model predicted it should manifest. The data points, meticulously plotted, seemed to gently curve away from the standard cosmological line, a subtle whisper of an alternative truth within the sprawling cosmos. It was far from a smoking gun yet, but it was enough to deepen their resolve and to push for even more refined analysis. They cross-referenced their findings with data from different telescopes and surveys, desperately searching for any systematic errors or biases in their own methodologies. The excitement within the team grew, tinged with a healthy dose of scientific caution. They understood that overturning such a colossal theory required not just compelling evidence, but overwhelming, irrefutable proof, and they were still very much in the early stages of gathering it. The universe, it seemed, was beginning to reveal its secrets, subtly, patiently, to those who dared to look beyond the obvious. The scientific community's initial reaction to the leaked preliminary findings was a mix of skepticism and subtle irritation. Rumors began circulating, fueled by disgruntled traditionalists who viewed Thorne and Petrova's work as a fringe assault on established science. Critics argued that the observed deviations were well within the margin of error, or attributable to unknown systematic biases in the observational data. They pointed to the immense success of the Big Bang model over decades, and the need for extraordinary evidence to challenge such a foundational theory. Online forums and scientific blogs buzzed with fierce debates, often descending into personal attacks and ad hominem arguments rather than substantive scientific discourse. Thorne and Petrova, however, largely ignored the noise. They understood that groundbreaking discoveries often face initial resistance. Their focus remained squarely on refining their analysis, gathering more data, and building an irrefutable case. They knew the battle for scientific truth was not won in the court of public opinion, but in the rigorous, unforgiving arena of empirical evidence and mathematical consistency. Their silence was not agreement. It was a testament to their unwavering dedication to methodical research. Thorne, anticipating the pushback, devised a series of null tests, experiments specifically designed to find no significant result if the Big Bang was correct, but a clear, measurable signal if CFIT held true. One such test involved analyzing the surface brightness of distant galaxies. In an expanding universe, distant galaxies should appear progressively dimmer not just because of distance, but because the expansion stretches their photons, diluting their light over a larger area. This effect is often called the surface brightness dimming or the Tolman surface brightness test. Thorne's CFIT predicted that while total flux would diminish with distance due to the interaction with cosmic fabric, the surface brightness per unit area would remain more constant or follow a different dimming law than predicted by the Big Bang, accounting for the cumulative redshift without spatial dilation. This was an incredibly challenging observation, as distant galaxies are inherently faint and difficult to resolve, but successfully performing this null test would provide a powerful, independent verification for a static universe, decoupling apparent dimming from actual expansion. It was a direct attack on one of the nuanced predictions of the Big Bang, a true test of the universe's ultimate nature. A critical aspect of Thorne's CFIT and his reinterpretation of cosmic phenomena involved a fundamental reevaluation of the concept of cosmic time. In the Big Bang model, time has a beginning, and the universe has a finite age of approximately 13.8 billion years. This timeline is crucial for understanding stellar evolution, galaxy formation, and the entire cosmic narrative. However, in Thorne's static universe, time stretches infinitely into the past. There is no definite cosmic clock, no singular moment of creation. This implied that stellar and galactic processes must operate over timescales that are potentially far, far longer than previously considered. Stars might live for trillions of years, galaxies evolve over periods incomprehensibly vast, and matter and energy cycle through cosmic processes perpetually. This radical shift in cosmic chronology had profound implications for our understanding of cosmic evolution, suggesting a universe that has always existed and will always exist, a timeless entity in a state of eternal being rather than a fleeting moment in a finite existence. It meant fundamentally restructuring our understanding of duration itself on the grandest cosmological scales, redefining what it truly meant for the universe to be. The challenges of rigorously testing Thorne's CFIT were immense. Observational biases, instrumental limitations, and the sheer vastness of cosmic distances introduced significant hurdles. Distant galaxies are inherently faint and small, making highly precise measurements of their angular size and surface brightness incredibly difficult. Light attenuation due to intergalactic dust, gravitational lensing distortions, and even the subtle effects of the Earth's atmosphere had to be meticulously accounted for and subtracted from the data. Petrova's team, armed with sophisticated algorithms and supercomputing power, spent countless hours developing new calibration techniques and statistical models to filter out noise and isolate the subtle signals predicted by CFIT. It was like trying to discern the exact shape of a distant mountain range through a persistent, thick fog. Each data point had to be scrutinized, each potential error source identified and mitigated. The process was slow, arduous, and often frustrating, pushing the boundaries of what was technologically possible in observational astronomy. Yet, with every refined calculation, with every incremental improvement in data quality, the subtle patterns predicted by Thorne's theory seemed to gain a little more statistical significance, deepening the mystery and the growing anticipation. Meanwhile, Thorne continued to refine the theoretical backbone of CFIT. He delved into the intricacies of quantum field theory and the nature of the vacuum. He posited that the fundamental mechanism for cosmic fabric interaction might lie in the zero-point energy of space-time itself, the inherent quantum fluctuations that exist even in seemingly empty space. Imagine the vacuum not as nothing, but as a sea of continuously forming and annihilating virtual particles, a turbulent quantum foam. Thorne hypothesized that photons, as they traversed this foam over gigaparsec distances, would experience cumulative, minute energy losses to this fluctuating quantum background, subtly stretching their wavelength. This wasn't merely a random interaction, but an intrinsic, directional effect, consistently pushing photons towards the red end of the spectrum in proportion to the distance traveled. He explored mathematical models where the effective refractive index of space itself subtly changed over vast scales, or where a previously unknown fundamental constant governed this photon fabric interaction. This wasn't just a new interpretation of observations, it was a profound shift in our understanding of spacetime, pushing the boundaries of quantum cosmology and challenging the very nature of empty space. The first truly compelling evidence for CFIT came from an unexpected source: studies of extremely ancient, massive elliptical galaxies. These galaxies, formed early in cosmic history according to the Big Bang model, should appear much smaller and brighter than their modern counterparts because they haven't had as much time to fully evolve and expand. However, Thorne's static universe predicted that these ancient galaxies, while still distant, wouldn't be subject to the same geometric size distortions caused by expansion. Petrova's team found that a significant number of these distant, evolved elliptical galaxies appeared larger and less dense than what the Big Bang model predicted for their redshift, aligning much more closely with Thorne's CFIT angular size predictions. It was a subtle yet statistically significant deviation, a persistent pattern that defied easy explanation within the standard model. This wasn't just about general observations. It was about specific types of galaxies, with known evolutionary paths that seemed to scream defiance at the expanding universe paradigm. The cosmic jigsaw puzzle was starting to click, piece by piece, into a different, unsettlingly static picture. The new findings from Petrova's team, though still preliminary, were too significant to ignore. They submitted a formal paper to a top-tier astrophysical journal, detailing their methodology, data analysis, and the observed deviations from Big Bang predictions, cautiously articulating how these findings aligned with Thorne's CFIT. The paper underwent an intense peer review process, subjected to unprecedented scrutiny by a panel of skeptical but fair-minded experts. Reviewers demanded additional analysis, robustness checks, and comprehensive responses to every conceivable objection. They pushed the team to the absolute limits of their scientific rigor. This was not merely an academic exercise. It was a public examination of a revolutionary claim. The tension was palpable. The scientific world held its breath, awaiting the verdict. Would this paper be published, signaling a legitimate challenge to cosmology's bedrock? Or would it be relegated to the realm of fringe theories? This was the trial by fire, the moment when Thorne and Petrova's quiet rebellion stepped into the unforgiving light of mainstream scientific discourse, ready to face the full weight of established wisdom. Against all odds, the paper was accepted and published. Its release sent shockwaves through the global scientific community. While the accompanying editorial stressed the need for further replication and independent verification, the mere publication in such a prestigious journal legitimized Thorne and Petrova's work far beyond the whispers of academia. Suddenly, physicists and astronomers worldwide were forced to grapple with a meticulously researched challenge to their fundamental understanding of the universe. Conferences that once ignored Thorne's theories now hastily added sessions to discuss them. Traditional cosmologists found themselves on the defensive, scrambling to find flaws in the new data or to formulate exotic explanations within the Big Bang framework. The abstract intellectual debates that had simmered for years now exploded into public discourse. Headlines screamed about a potential cosmic paradigm shift or the end of the Big Bang. The scientific method, a relentless pursuit of truth above all else, was playing out on the grandest stage, forcing a re-evaluation of cosmic proportions. The immediate aftermath of the paper's publication saw a frantic race to replicate Thorne and Petrova's findings. Research groups from institutions across continents, some initially skeptical, others intrigued, launched their own analyses using different telescopes, independent datasets, and varied methodologies. This was the ultimate crucible of scientific validation, independent verification. Telescopes like the Subaru telescope, the European Southern Observatory's Very Large Telescope, and eventually even data from the Hubble Space Telescope and fledgling James Webb Space Telescope missions, were repurposed or reanalyzed to search for the subtle angular size deviations and surface brightness anomalies predicted by CFIT. The astronomical community, though initially resistant, exhibited its greatest strength: self-correction through rigorous empirical testing. If the results held, the universe would never look the same again. Every negative result would reinforce the Big Bang. Every positive one would deepen the mystery of expansion and further validate Thorne's radical vision. The initial replication efforts yielded mixed results. Some teams found hints of the same deviations, though often with larger error bars. Others found no statistically significant departures from the Big Bang predictions. The scientific debate became even more heated, with intense arguments over data calibration, statistical methodologies, and the interpretation of marginal results. It was a battlefield of footnotes and p-values. Thorne and Petrova meticulously reviewed every replication attempt, engaging with critics, offering guidance on data handling, and often identifying subtle biases or calibration errors in the dissenting studies. They published detailed rebuttals, not to shut down debate, but to refine the discussion, focusing on the specific conditions under which their predicted effects would be most prominent and least susceptible to noise. The scientific process, often slow and painstaking, was unfolding in real time, messy and contentious, but ultimately self-correcting. The truth, whatever it was being forged in the fires of intense intellectual scrutiny, slowly emerging from the clamor of conflicting data points and passionate arguments. The tide began to turn with the release of data from a new generation of wide-field surveys and the initial deep-field observations from the James Webb Space Telescope. These instruments, designed for unprecedented sensitivity and spatial resolution, peered further back in cosmic time and space than ever before, revealing incredibly faint, distant galaxies with astonishing clarity. This new, pristine data allowed Petrova's team to significantly reduce uncertainties and biases that plagued earlier observations. They were able to confirm, with much higher statistical confidence, the subtle but persistent deviations in angular size and surface brightness of distant galaxies, exactly as predicted by Thorne's CFIT. The data simply did not fit the Big Bang model's expectations for these ancient distant structures. A profound sense of unease settled over the cosmological community. The anomalies, once dismissed as statistical quirks, were now undeniable empirical facts, forcing an uncomfortable re-evaluation of foundational principles. The universe was starting to whisper a different narrative, one that defied the narrative of cosmic expansion. For many cosmologists, this was the moment of truth. The new, undeniable data from JWST became the ultimate arbiter. It wasn't just small discrepancies anymore. It was a consistent, statistically robust dataset that consistently showed galaxies behaving in a way that contradicted the fundamental scaling laws of an expanding universe. The Big Bang model, while explaining so much, simply couldn't accommodate these new observations without introducing an ever-increasing number of ad hoc assumptions or pushing its foundational parameters to their absolute limits. The intellectual discomfort was palpable. Scientists pride themselves on their ability to adapt to new evidence, but overturning a paradigm as deeply ingrained as the Big Bang was akin to rewriting a sacred text. The debates escalated from academic journals to major scientific conferences, where presentations on Thorne's CFIT were now front and center, drawing massive crowds. The scientific discourse became less about polite disagreement and more about an existential crisis for cosmic understanding, as the universe itself seemed to refuse to conform to humanity's grandest, most accepted narrative of its own creation. Dr. Thorne and Dr. Petrova, once seen as fringe theorists, were now at the epicenter of a scientific revolution. They calmly presented their overwhelming evidence, methodically addressing criticisms and patiently explaining the intricacies of CFIT. Thorne articulated the elegance of a static universe, where the redshift was an intrinsic property of light's journey through space, rather than a sign of universal expansion. Petrova detailed the statistical robustness of their angular size and surface brightness data, demonstrating how these observations could only be explained by a non-expanding cosmos. Their presentations were not triumphalist, but rather imbued with a profound sense of scientific awe and humility, acknowledging the vastness of the challenge they faced in overturning a century of established thought. They emphasized that science was a continuous process of discovery and refinement, and that even the most successful theories must yield to compelling new evidence. It was a powerful display of scientific integrity, ushering in not just a new model of the universe, but a new era of cosmic humility and open-mindedness. The reinterpretation of the cosmic microwave background became a critical turning point. Thorne's original hypothesis, that the CMB was an intrinsic property of his cosmic fabric, rather than a Big Bang afterglow, gained surprising traction. New theoretical work independent of Thorne began to emerge, describing how a static universe, filled with some form of pervasive energetic medium or in a state of radiative equilibrium, could naturally produce a perfect blackbody spectrum at 2.7 Kelvin, precisely matching the CMB. Some propose that it was the residual energy from continuous localized creation events or cycles of matter and energy that maintained universal equilibrium. Others explored the idea of a truly eternal universe where stars and galaxies are continuously born and die, maintaining a constant energy density that radiates as a background. The consistency of the CMB, once the strongest argument for the Big Bang, was now shown to be equally, if not more, consistent with a static, perpetually existing cosmos. This was a profound philosophical shift, eliminating the need for a singular moment of creation and introducing the radical notion of a universe without beginning or end, a truly eternal entity. With the expanding universe model facing severe challenges from multiple observational fronts, the once minor riddle of the Hubble tension transformed into a glaring inconsistency. Different measurement methods continued to yield different expansion rates, a problem stubbornly resistant to explanation within the Big Bang framework. However, within Thorne's CFIT, this tension simply vanished. If the universe wasn't expanding at all, then measured expansion rates were merely artifacts of the light fabric interaction. The slight variations derived from different distance measuring techniques, whether through supernovae or CMB data, could now be reinterpreted as slightly different manifestations of how photons interact with the cosmic fabric at varying distances and energies, rather than representing distinct expansion rates of space itself. This offered a clean, elegant solution to one of cosmology's most persistent headaches, turning a perplexing anomaly into a natural consequence of a static cosmos. The universe, it seemed, was not in a state of conflicting expansion rates, but rather in a state of eternal stillness, its observed dynamics merely an elaborate optical illusion, caused by the subtle, previously unnoticed properties of the very space through which we observe. The concept of, quote, dark energy, the mysterious force thought to be accelerating the universe's expansion, was the next casualty. With Thorne's CFIT, the observed dimming of distant type Ia supernovae, previously the primary evidence for dark energy, was naturally explained without any need for such an enigmatic component. If photons progressively lost energy and redshifted due to interaction with the cosmic fabric, they would intrinsically appear dimmer over vast distances, mimicking the effect of accelerated expansion. This provided a far more parsimonious explanation for the supernova data, eliminating the need for over 70% of the universe's energy content to be composed of an unseen, undetectable, and purely theoretical entity. It effectively streamlined the cosmic inventory, replacing a profound mystery with the direct consequence of light's journey through a static, interacting space. The universe suddenly became much simpler, much more elegant, and infinitely more comprehensible, shedding its mysterious, dark constituents and revealing its true quiescent nature, free from the dictates of an invisible, repulsive force. The implications of a static universe for the existence of parallel universes, or the multiverse theory, were profound. While modern cosmology, particularly inflationary models within the Big Bang framework, sometimes lends itself to the idea of an endless cosmic tapestry of separate universes, Thorne's static universe presented a different picture. In a universe without a beginning or end, a universe that has always been and always will be, the very notion of a birth event repeated countless times across a multiverse becomes less compelling. Instead, the universe might be a singular, eternal entity, perhaps finite in size, but unbounded in time, or even truly infinite in its extent, a grand, singular reality rather than one of a myriad. This shifted the focus from creation events to the inherent properties of reality itself, prompting new philosophical debates about uniqueness versus multiplicity in the cosmos. It raised the possibility that perhaps we are not just one bubble among many, but part of a singular, vast, and timeless whole, forever existing and evolving within its own inherent, unchanging boundaries. The revelation of a static universe necessitated a complete reevaluation of stellar evolution and galaxy formation. If the universe had always existed, then stars and galaxies have had effectively infinite time to form, evolve, and cycle through generations. This meant that the oldest observed stars and galaxies didn't necessarily represent the first generations from a Big Bang, but merely some of the oldest surviving structures. It allowed for a much more diverse and complex history of cosmic structures, with mechanisms for continuous star formation and matter recycling operating over eons. The distribution of elements would be a result of countless stellar lifetimes, supernovae, and cosmic recycling efforts, rather than a single primordial burst of nucleosynthesis. This opened up fascinating new avenues for astrophysical research, prompting scientists to explore how the universe could sustain continuous creation and renewal, how galaxies could self-regulate their star formation over potentially infinite timescales, and how matter and energy could perpetually cycle through cosmic processes without beginning or end. It implied a universe that was a living, breathing, self-sustaining entity, constantly regenerating its constituents. The philosophical implications of a static, eternal universe were profound. For generations, humanity wrestled with the concept of a universe that had a beginning, questioning what came before the Big Bang, and contemplating its ultimate end. A gradual cooling, a fiery crunch, or a lonely expansion into nothingness. Thorne's CFIT offered a radical alternative, a universe that simply is. No beginning, no end. This meant that the universe was not a fleeting phenomenon within a greater emptiness, but rather the ultimate and perpetual reality itself. It challenged our human-centric understanding of time and existence, suggesting that our intuitive linear progression of birth, life, and death might not apply to the cosmos as a whole. This shifted our existential questioning from, where did it come from, to, what is its inherent nature, and, quote, what does it mean to be a transient part of an eternal whole? It was a concept that inspired both a deep sense of awe and a quiet, unsettling realization of humanity's smallness within a truly boundless and timeless reality, yet also an inherent connection to an eternal and unchanging cosmic flow. The acceptance of CFIT wasn't instantaneous or universal. Pockets of resistance remained strong, particularly among older cosmologists who had dedicated their lives to the Big Bang model. They continued to search for flaws in Thorne and Petrova's data, to propose alternative explanations for the observed anomalies within the Big Bang framework, or to simply express a profound disbelief in such a radical shift. Some argued that discarding the Big Bang removed a clear, testable origin point, making cosmology less predictive. Others questioned the elegance of a universe with inherent photon-fabric interactions, finding it less aesthetically pleasing than pure metric expansion. This intellectual struggle underscored a fundamental truth about scientific progress. New ideas rarely triumph through gradual acceptance, but rather by demonstrating superior explanatory power and predictive accuracy, often outliving dissenting arguments. The younger generation of scientists, unburdened by decades of professional investment in the Big Bang, were more open-minded, eager to explore the implications of CFIT and to embrace the new frontier it promised. The scientific torch was passing, slowly but inexorably, to a new understanding of the universe. The shift towards a static universe paradigm had far-reaching implications beyond just astrophysics. It affected theoretical physics, inspiring new investigations into the fundamental nature of space-time, gravity, and quantum mechanics. How did the cosmic fabric interact with photons at a quantum level? Did this fundamental property of space have implications for other forces or particles? Could it lead to a unified theory of everything that previously seemed out of reach? New theoretical models began to incorporate Thorne's core idea, exploring the possibility of fundamental constants that were not constant over cosmic distances, or the existence of subtle, pervasive fields that permeated and modified the vacuum itself. The search for a theory of quantum gravity now had a new direction, perhaps suggesting that the very large scale of the universe and the very small scale of quantum physics were intrinsically linked by this previously unknown interaction. This newfound understanding prompted a renaissance in theoretical physics, pushing the boundaries of human knowledge and suggesting that the universe held far more intricate and elegant secrets than previously imagined, all hidden within the seemingly empty void of space. The very nature of singularities, the infinitely dense points at the heart of black holes, and, in the Big Bang model, the genesis of the universe, came under renewed scrutiny. If the universe didn't begin as a singularity, what did that imply for black holes? Some physicists began to explore how Thorne's cosmic fabric interaction might affect gravitational fields at extreme densities, or if a true singularity was even possible in a universe structured by CFIT. Perhaps black holes, rather than leading to an infinite density point, were regions where the cosmic fabric itself became so extreme that it altered the local laws of physics in profound ways, but without hitting true infinities. This reevaluation opened up new mathematical doorways, allowing for alternative models of black hole interiors, and perhaps even providing a mechanism for them to eventually dissolve or interact with the cosmic fabric in a way that prevented infinite densities. It was a fascinating new frontier, suggesting that our most extreme cosmic objects might also be subtly shaped by the pervasive, interactive fabric of space, further integrating all aspects of the universe into a cohesive, non-expanding whole. The shift to a static universe also prompted a re-examination of our place within the cosmos. If there was no finite beginning point and no ultimate end, then humanity's existence wasn't a fleeting moment in a burgeoning universe, but rather a temporary flicker within an eternal, unchanging grand design. This perspective led to new philosophical debates concerning cosmic purpose or lack thereof, the meaning of consciousness in an infinite timeline, and indeed the very definition of life on cosmic scales. Are we unique, or is life continuously emerging throughout an eternal cosmos? Does intelligence arise and disappear over eons in countless star systems, a perpetual cycle of cosmic cognition? This profound existential pondering moved beyond mere scientific inquiry into the realms of theology, philosophy, and even art, deeply influencing human perception of reality. It demanded a new form of cosmic humility, recognizing our tiny, ephemeral existence within an infinitely vaster, timeless whole, challenging humanity to find new meaning in eternity rather than in ephemeral beginnings and ends. The legacy of Edwin Hubble, Georges Lemaitre, and the pioneers of the Big Bang wasn't erased. It was recontextualized. Their observations and theoretical frameworks remained profoundly important, but their interpretations were now viewed through a different lens. Hubble's law still described the observed recession of galaxies, but that recession was redefined as a misinterpretation of light's interaction with the cosmic fabric, rather than actual spatial expansion. The CMB was still a crucial background radiation, but its origin was shifted from a primordial fireball to an intrinsic property of the static universe. This was not a negation of their brilliant work, but an evolution, a deeper understanding built upon their initial groundbreaking discoveries. Future textbooks would tell a new story, one where the universe was revealed to be a timeless, perpetually existing entity, its apparent expansion, a grand, fascinating illusion, and its true nature uncovered by those daring enough to challenge the most deeply held beliefs. It was a testament to the self-correcting nature of science, where even the most fundamental truths can be refined and rewritten in the relentless pursuit of deeper understanding. Public engagement with the new understanding of the universe soared. Documentaries, popular science books, and educational programs rapidly shifted to explain the concept of a static universe and Thorne's cosmic fabric interaction theory. The public, often fascinated by stories of scientific revolution, embraced the idea of a universe that was stranger and more mysterious than previously thought. Discussions about cosmology moved from academia to living rooms, inspiring a new generation of aspiring scientists and sparking widespread curiosity about the true nature of reality. The profound implications for humanity's place in the cosmos were widely debated, capturing the imaginations of millions. It illustrated that science, at its core, is a human endeavor, constantly pushing the boundaries of knowledge, and that even the most established truths are open to re-examination in the face of compelling new evidence. The universe, once a distant, abstract concept for many, became a subject of renewed wonder and widespread fascination, igniting a hunger for knowledge about its timeless, unchanging depths. Years after its initial publication, Thorne's cosmic fabric interaction theory, once a radical fringe idea, had moved firmly into the mainstream. It wasn't just an alternative. It was the new accepted paradigm, supported by an overwhelming body of evidence. Future missions were designed specifically to explore the properties of the cosmic fabric, to measure its fluctuations with unprecedented precision, and to understand its quantum mechanical underpinnings. The scientific community, once deeply divided, rallied around this new, more elegant understanding of the cosmos. New theories of gravity, quantum mechanics, and particle physics began to emerge, all subtly shaped by the implications of a static, interacting universe. The universe, it turned out, was not expanding. It was a grand, timeless, and subtly dynamic entity, its true nature hidden in plain sight, mimicking expansion through the most fundamental interaction of light with its very being. This fundamental shift irrevocably altered humanity's perception of reality, unveiling a universe far more profound, intricate, and eternally self-renewing than any Big Bang ever dared to contemplate. The triumph of CFIT wasn't just about overturning the Big Bang, it was about opening entirely new avenues of scientific inquiry. Now that the true nature of the cosmic fabric was beginning to be understood, scientists could start exploring the profound implications for other fundamental forces. Did gravity, for instance, also interact with this fabric in a subtle way, perhaps explaining phenomena currently attributed to dark matter? Thorne's initial work on redshift and dimming was just the tip of the iceberg. The very constants of nature, like the gravitational constant or the fine structure constant, could potentially be re-evaluated for their behavior within this new cosmic medium. Perhaps what we perceive as universal constants are, in fact, subtly modulated by this omnipresent fabric over vast scales or long durations. This introduced an exciting uncertainty and a vast new landscape for exploration, prompting rigorous experimental and theoretical studies. The search for evidence for this fabric interaction, for gravity or other fundamental forces, became the new holy grail for experimental physicists, pushing the boundaries of observational precision. One of the most intriguing new research directions involved the prospect of cosmic communication over immense distances. If light's interaction with the cosmic fabric was indeed the source of redshift, rather than uniform expansion, it raised fascinating questions about how advanced civilizations might communicate or detect each other across gigaparsecs. Would their signals be distorted in new ways, Or would the very interaction with the fabric facilitate unforeseen methods of information transfer? Some theoretical physicists began to explore the possibility that the quantum foam, or cosmic fabric, could potentially be manipulated at a fundamental level, allowing for communication that bypassed traditional relativistic speed limits, or even enabling a form of cosmic resonance for detecting distant, advanced technological signatures. This was highly speculative, bordering on science fiction, but the door had been opened by CFIT to rethink the basic principles of interstellar communication. The universe, no longer constrained by the limits of a simple expanding void, suddenly seemed ripe with possibilities for new forms of interaction, creating an exciting frontier for astrobiology and SETI research. The concept of dark matter, another enigmatic component of the Big Bang model, also faced a profound reevaluation. Dark matter, an invisible substance thought to make up the vast majority of matter in the universe, was invoked to explain phenomena like the anomalous rotation curves of galaxies and the gravitational lensing of distant objects, effects that couldn't be accounted for by visible matter alone. However, with CFIT now establishing an active cosmic fabric, some physicists began to speculate that the observed gravitational anomalies might not require additional unseen matter. Instead, they proposed that the cosmic fabric itself, or its interaction with gravity, might subtly modify gravitational fields on galactic scales, producing effects previously attributed to dark matter. This was a monumental leap, suggesting that perhaps the universe contained far less missing mass than previously thought, and that our understanding of gravity itself might need adjustment, not just the introduction of new, exotic particles. This opened the scientific door to models of modified gravity that had once been considered fringe, now potentially reviable under the new cosmological paradigm. The new understanding of a static universe demanded a complete overhaul of cosmological simulations. Previous simulations painstakingly modeled the expansion of space, the growth of structures within that expansion, and the cooling of the early universe. Now, these models had to be rewritten from the ground up, to account for a universe where structures formed and evolved over potentially infinite timescales within a non-expanding medium. This meant reevaluating the initial conditions of the universe, the processes of galaxy merger and evolution, and the long-term stability of cosmic structures. New algorithms were developed to simulate the intricate interactions of light and matter with the cosmic fabric, predicting the precise redshifts and apparent dimming of distant objects without invoking spatial expansion. This was a monumental computational undertaking, pushing the boundaries of supercomputing power, but it was essential to fully explore the implications of CFIT and to generate new, testable predictions. The universe was being computationally reborn, its past and future reimagined within the immutable embrace of a static, timeless existence. The historical context of the redshift controversy was re-examined with renewed interest. Before Hubble definitively linked redshift to expansion, other explanations were posited. Some, like the tired light hypothesis, suggested that photons simply lost energy as they traveled through space. Thorne's CFIT, while distinct, shared some philosophical kinship with these earlier ideas in challenging the expansion dogma. Historians of science revisited old debates, examining why certain theories gained dominance while others faded into obscurity. They explored the subtle biases, the prevailing philosophical trends, and the limitations of observational technology that shaped our understanding of the universe. This retrospective analysis offered valuable lessons about the scientific process, demonstrating how entrenched paradigms can resist change, even in the face of subtle anomalies, and how often breakthroughs come from re-evaluating fundamental assumptions. The history of cosmology, once a linear progression towards the Big Bang, was now a more nuanced narrative of diverging paths, missed opportunities, and the eventual triumph of a more profound truth, unearthed by persistent, unconventional inquiry. The very concept of absolute rest in the universe, long considered a problematic notion in relativistic physics, acquired a new dimension within the static universe model. If space itself was not expanding, then perhaps there was a cosmic frame of reference, a universal state of stillness relative to which all motion could be measured. This wasn't about a return to a pre-Einsteinian ether, but rather a reconceptualization of the cosmic fabric as an inherent, fixed background. How would this absolute cosmic frame interact with the principles of special and general relativity, which largely eschew absolute motion? These questions sparked intense theoretical debates, forcing physicists to explore new interpretations of space-time. It pushed the boundaries of our understanding of motion, challenging the very idea of relativity as the ultimate arbiter of velocity and offering a philosophical anchor point in a universe that had previously seemed utterly devoid of any fixed reference. What would it mean for humanity to discover an absolute cosmic stillness, a true foundation upon which all other movements were fundamentally relative? The search for new phenomena that could only be explained by the cosmic fabric interaction theory became a primary focus for experimental physicists. They sought to design ultra-high precision experiments to detect the subtle energy exchange between photons in the quantum vacuum, or to verify variations in fundamental constants over extremely precise laboratory conditions, potentially mimicking the vast cosmic interactions. This required entirely new types of detectors, pushing the limits of sensitivity and precision. Could a powerful laser beam, sent through a supercooled vacuum over a long distance, exhibit a minute, predicted redshift? Could highly sensitive atomic clocks show subtle, time-dependent variations in a laboratory setting when exposed to controlled, extreme conditions designed to amplify the fabric interactions? These were incredibly challenging experiments, demanding unprecedented control over environmental factors and the elimination of all known sources of noise. But the potential payoff, a direct laboratory confirmation of CFIT, would be the ultimate empirical validation, solidifying the new paradigm beyond any doubt. The universe's grand illusion was now being dissected in the most minute, precise ways possible. Theoretical cosmologists began developing new origin stories for a static universe. Rather than a singular Big Bang, they explored models of continuous creation and destruction, a perpetually recycling cosmos where matter and energy are endlessly transformed. Some hypothesized that the universe might exist in a state of perpetual equilibrium, where the formation of new stars and galaxies is balanced by the eventual decay of old ones, ensuring a constant, unchanging cosmic density. Others considered a cyclical universe far grander than previously conceived, one that undergoes phases of contraction and apparent expansion without ever hitting a true singularity, perhaps driven by the intrinsic properties of the cosmic fabric itself. These speculative models, while still in their infancy, offered a rich tapestry of possibilities for a universe without a genesis, a cosmos that has always been and always will be, maintaining its state through inherent, self-regulating processes. This was a profound philosophical shift, moving away from a single, dramatic beginning to an eternal, cyclical dance of cosmic proportions, reshaping our deepest notions of creation and existence into a timeless, self-sustaining flow. The search for extraterrestrial intelligence, SETI, also experienced a renaissance. If the universe was static and potentially infinite in time, the probability of life emerging and evolving elsewhere increased exponentially. It meant that life wasn't a rare, fleeting phenomenon in a rapidly expanding and cooling universe, but a potential constant, arising repeatedly over eons in countless star systems. This shifted SETI's strategy from searching for short-lived, transient signals from nascent civilizations to looking for persistent, ancient patterns of technological activity, potentially spanning billions of years. Advanced civilizations, if they existed, might have had vastly more time to develop, to spread across their static galaxies, and to even leave enduring technological artifacts or send messages across the timeless cosmic fabric. This opened up thrilling possibilities for future exploration, inspiring new methods of searching for techno-signatures, and encouraging a deeper consideration of the long-term survival and evolution of intelligence within an eternal cosmic tapestry. The universe, no longer constrained by a finite lifespan, became a boundless canvas for the perpetual emergence of life and intelligence. The scientific curriculum, from university physics departments to high school science classes, underwent a dramatic transformation. Textbooks were rewritten, removing chapters on the Big Bang and introducing the principles of cosmic fabric interaction theory. Students learned about the static universe, its subtle interactions with light, and the profound implications for time, gravity, and existence. New graduate programs emerged, specializing in CFIT and its related fields, fostering a new generation of scientists intimately familiar with this revolutionary paradigm. This educational shift ensured that the new understanding would be deeply embedded in the minds of future researchers, preventing a return to old ideas. It was a testament to how quickly science can adapt and evolve when confronted with undeniable evidence, reshaping not just our knowledge, but the very way we educate and inspire future generations to explore the deepest mysteries of reality. The universe, once confined to a linear, explosive past, was now unveiled as a truly timeless and boundless entity, beckoning new minds to unlock its ancient, unchanging secrets. The reinterpretation of cosmic redshift as an intrinsic property of light's journey through the, quote, cosmic fabric, rather than a Doppler effect from expansion, led to a renewed focus on the fundamental nature of light itself. If photons constantly exchanged minute amounts of energy or interacted with the quantum vacuum, what did that imply for their wave-particle duality? Did it affect entanglement over cosmic distances? New quantum optics experiments were proposed to probe these incredibly subtle interactions in controlled laboratory settings, trying to replicate the micro-level effects that, when accumulated over billions of light-years, cause cosmic redshift. This was a frontier where quantum mechanics met cosmology, pushing the boundaries of our understanding of light. It demanded physicists to think beyond the conventional models of photon propagation and to consider a universe where light was not merely a messenger, but an active participant in shaping cosmic appearances, its very nature subtly altered by the pervasive, energetic medium of space itself. This was a profound and exciting challenge, bridging the largest and smallest scales of physical reality. The implications of CFIT extended to our understanding of the universe's ultimate fate. In the Big Bang model, the future of the universe depended on the interplay of dark energy and matter density, leading to scenarios like the Big Freeze, eternal expansion and cooling, the Big Rip expansion tearing everything apart, or the Big Crunch gravitational collapse. However, in a static universe, these dramatic endings were rendered obsolete. The universe, having no beginning, likely has no end. It would simply continue to exist, unchanging in its fundamental structure, with matter and energy perpetually cycling through stars, galaxies, and perhaps even some cosmic recycling mechanism. This offered a sense of cosmic stability, a profound reassurance that the universe was not hurtling towards an inevitable chilling demise or a violent implosion. Instead, it would simply be, eternally, a boundless stage for the continuous unfolding of physical processes, a grand, perpetual motion machine, forever maintaining its state without requiring a dramatic cosmic finale. The question of cosmic homogeneity and isotropy also garnered renewed examination under the CFIT paradigm. The cosmological principle, a fundamental assumption in the Big Bang model, states that the universe is roughly the same everywhere and in all directions on large scales. While observations largely support this, some anomalies like the axis of evil in the CMB or unexpected large-scale alignments of quasars have occasionally challenged it. In a static universe, these anomalies might be viewed differently. Perhaps they are not mere statistical flukes or observational errors, but subtle indicators of underlying, non-uniform properties of the cosmic fabric in specific regions, or local gravitational influences within a globally static framework. This opened up the possibility that the universe, while broadly homogeneous, might possess intricate, subtle structures or variations on the very largest scales, waiting to be discovered. It nudged cosmologists to look for finer details and more nuanced patterns, moving beyond broad generalizations to uncover the rich, hidden complexity of a non-expanding yet internally dynamic cosmos. The advent of quantum computing provided new tools for exploring the intricate details of the cosmic fabric interaction theory. Simulating the interaction of individual photons with the quantum vacuum over cosmic distances, once computationally insurmountable, became increasingly feasible. Quantum algorithms could model the subtle energy exchanges, the wave function collapse, and the cumulative redshift effects with unprecedented precision. This allowed theoretical physicists to refine their mathematical models of CFIT, exploring minute variations in the fabric's properties and testing how they correlated with observed cosmic phenomena. It moved the theory from abstract mathematical frameworks to tangible, testable simulations, allowing scientists to virtually observe light traveling through a static universe and confirm its predicted behavior. This fusion of cutting-edge computing with cosmological theory promised to unlock even deeper secrets of the cosmic fabric, confirming its existence and its role in shaping the universe's perceived dynamics, providing a profound new level of understanding of space itself. The human brain's capacity to conceptualize vast scales of time and space was profoundly challenged by the static universe. In an expanding universe with a beginning and an end, our minds, accustomed to linear narratives, could at least grasp its finite nature. But a universe that has always existed and will always exist forces a different kind of cognitive leap. How do we, as finite beings, truly comprehend eternity? This philosophical and psychological challenge led to new interdisciplinary research, blending cognitive science with cosmology. Neuroscientists explored how the human brain processes infinite concepts, while philosophers debated the implications for human purpose and meaning in a timeless cosmos. It pushed beyond mere scientific understanding into the very fabric of human consciousness, asking fundamental questions about our perception of time and our place in an eternal reality. The universe, it seemed, was not just expanding our knowledge, but fundamentally expanding the very boundaries of our perception and consciousness itself, forcing us to rethink our place in limitless duration. One of the long-standing cosmological debates, the so-called arrow of time, also gained new perspectives. In the Big Bang model, the expansion of the universe often served as the cosmological arrow, defining the direction of time from a singular, low-entropy beginning to an ever-increasing entropy future. In a static universe, this explanation vanished. What then defined the direction of time? Was it purely a thermodynamic phenomenon, where entropy always increases locally, but the universe as a whole remained in a state of eternal equilibrium? Or did the omnipresent cosmic fabric itself possess an inherent temporal directionality, subtly guiding the flow of time? This prompted a deep re-examination of thermodynamics, quantum mechanics, and the philosophical underpinnings of time itself. The discussion moved beyond the simple notion of an expanding space as the driver of time's direction, opening up complex questions about the fundamental origins of irreversibility and the nature of conscious experience within a timeless or perpetually cycling cosmos. The universe, it seemed, was not merely dynamic in its spatial dimension, but in its very definition of temporal progression. The search for gravitational waves, ripples in space-time predicted by Einstein, continued to be a crucial area of research. While their detection in the Big Bang model provided further confirmation of general relativity and extraordinary cosmic events, in a static universe, their interpretation might shift. The cosmic fabric interaction theory suggested that the fabric itself was active. How would massive cosmic events, like black hole mergers, generate these ripples within an already active fabric? Would the fabric's properties affect how gravitational waves propagate over vast distances, perhaps leading to subtle distortions or attenuations? New theoretical work explored deviations from general relativity at cosmic scales, seeking to incorporate the CFIT framework into our understanding of spacetime curvature and dynamic gravitational phenomena. It was a fascinating confluence of groundbreaking observation and revolutionary theory, where the detection of cosmic ripples could now provide new insights into the subtle, energetic properties of the very fabric of reality, confirming its active role rather than just its passive curvature. The ultimate fate of all matter within a static, eternal universe also became a subject of intense scientific and philosophical contemplation. If the universe had no end, what would happen to stars, galaxies, and even black holes over truly infinite timescales? Would protons eventually decay, leading to a heat death? Or would the cosmic fabric itself provide a mechanism for rejuvenation, perhaps through continuous creation of new particles or energy from the vacuum? Some theorists proposed that the pervasive cosmic fabric could act as a source or sink for matter and energy, maintaining a perpetual balance over cosmic epochs, ensuring the universe never truly dies, but simply evolves in different forms. This offered a more optimistic view than the Big Bang's heat-death scenario, suggesting that the universe was truly eternal, a grand, self-sustaining system, constantly recycling its components and perpetually generating new forms of existence, without ever running out of fuel or succumbing to ultimate entropy. The paradigm shift from an expanding to a static universe highlighted the profound influence of human assumptions on scientific models. For decades, the initial interpretation of redshift as unequivocally due to motion rather than an intrinsic property of light-space interaction profoundly shaped the Big Bang model. This realization served as a powerful lesson in scientific humility, reminding researchers to constantly question even the most foundational assumptions and to remain open to alternative interpretations of observational data. It underscored the importance of methodological pluralism, encouraging scientists to explore diverse theoretical frameworks and to avoid premature closure on complex cosmic questions. The universe, it turned out, was not just expanding our knowledge, but expanding our understanding of the inherent biases and assumptions that can shape even the most rigorous scientific inquiries. This realization fostered a new era of critical thinking and intellectual openness within the scientific community, ensuring that future advancements would be built upon even stronger and more rigorously examined foundations. The discovery and validation of Thorne's cosmic fabric interaction theory has irrevocably altered humanity's relationship with the cosmos. No longer are we merely fleeting inhabitants of a universe born from an explosion and destined for a cold death. Instead, we are part of an eternal, timeless reality, a subtle, dynamic tapestry where light itself bears the imprint of its journey through the very fabric of existence. The universe never expanded. It simply is, a grand, infinite, and endlessly fascinating entity, its secrets slowly revealing themselves to those who dared to question, to observe, and to imagine beyond the confines of accepted truth. This radical shift, born from meticulous observation and bold theory, stands as a testament to the enduring power of scientific inquiry and humanity's ceaseless quest to understand its place within a cosmos far more wondrous and mysterious than we ever dared to dream, now standing still, vast, and eternally profound. The scientific exploration of the cosmic fabric itself became a primary research endeavor. What was it precisely? Was it a quantized field, a manifestation of quantum gravity, or something entirely new? Theorists proposed various models. Some suggested it was the zero-point energy field, previously thought to be a passive background, now understood as an active, interactive medium. Others explored the idea of a fundamental space-time fluid, with inherent, subtle viscosities or refractive properties at cosmic scales. Experiments were conceived to probe its properties, such as searching for infinitesimal variations in the speed of light over ultra-long baselines, or measuring minute shifts in the energy of gamma rays arriving from distant cosmic events. This new research frontier ventured beyond traditional particle physics, delving into the very microstructure of space-time, questioning if the vacuum itself was an energetic entity whose subtle properties were responsible for the grand cosmological illusion of expansion. The once empty void of space was now revealed to be a vibrant, active, and fundamental player in the universe's true nature. The re-evaluation of the early universe in a static, non-expanding model posed significant challenges and opportunities for theoretical physics. Without a hot Big Bang, how did the initial conditions of the static universe arise? Some theories explored extreme, high-energy states, where matter and energy were in a perpetual state of creation and annihilation, maintaining a uniform density. Others proposed that the universe had always existed in its current general form, with matter and energy continuously recycling through cosmic processes over infinite eons. This necessitated new mathematical formalisms to describe such a timeless state, exploring concepts like eternal inflation, but reinterpreted without the bang, or models based on a stable, self-sustaining quantum vacuum. The universe's perceived age was now infinite, and its true genesis was not a singular event, but perhaps an inherent property of its everlasting existence. This was a profound conceptual shift, prompting physicists to fundamentally reconsider the very question of beginning itself when applied to the cosmos, opening up a universe that had always been and always would be, timelessly existing. The precise calibration of distance measurements in a static universe became critical. While Type Ia supernovae still served as essential standard candles, their observed dimming was now understood to be a direct consequence of light's interaction with the cosmic fabric, rather than an accelerating expansion. This meant revising the supernova luminosity distance calculations, removing the dark energy component, and incorporating the CFIT interaction parameter. This also applied to other distance indicators, like Cepheid variables. The new understanding allowed for more accurate measurements of cosmic distances, as they no longer depended on a model of expansion that was now being questioned. This sharpened our ability to map the universe, revealing its true spatial distribution more accurately without the distortion caused by the illusion of expansion. It was a painstaking, yet vital process that solidified the empirical basis of CFIT and provided the most accurate spatial map of the universe to date, unveiling its true structures with unprecedented clarity. The question of whether the cosmic fabric itself had a definite temperature or energy distribution, beyond just the inherent background, became an intriguing research area. If the CMB was an intrinsic property of this fabric, what other thermal signatures might it possess? Could it subtly interact with other forms of radiation or particles, leading to new, observable phenomena? Some theorists speculated about faint, long-wavelength cosmic fabric noise that might be detectable with next-generation radio telescopes or neutrino observatories. This would be distinct from the CMB, perhaps revealing specific modes of energetic oscillation within the fabric itself. Such detections would provide direct, empirical evidence for the physical reality of the cosmic fabric, moving it from a theoretical construct to a measurable entity. It was an ambitious undertaking, requiring technological breakthroughs in detector sensitivity, but the potential to truly listen to the hum of the universe's underlying structure was a powerful motivator, promising to unveil the hidden symphony of spacetime itself. The reinterpretation of cosmic redshift also prompted a re-evaluation of distant quasars. These incredibly luminous galactic nuclei, often observed at very high redshifts, had always been considered among the earliest and most energetic objects in the universe. In the Big Bang model, their high redshift indicated their immense distance and young age. However, in a static universe, their redshift was purely an artifact of light's long journey through the cosmic fabric. This meant that quasars were not necessarily young objects in a nascent universe, but perhaps merely intrinsically bright objects that could exist at any cosmic epoch. Their extreme luminosity and compact size still pointed to supermassive black holes accreting matter, but their temporal placement in cosmic history became a matter of ongoing research, decoupled from a strict age-redshift relationship. This challenged the accepted narrative of quasar evolution, opening up new models for their formation and distribution in a timeless cosmos, pushing for a deeper understanding of their physics rather than relying on cosmological assumptions about their age. The cosmic web, the intricate large-scale distribution of galaxies, clusters, and voids, also offered new insights for CFIT. In the Big Bang model, this web forms from the gravitational collapse of primordial density fluctuations within an expanding universe. In a static universe, gravity still played the primary role, but the formation processes would unfold over potentially infinite timescales, without the diluting effect of expansion. This meant that the universe's large-scale structure could be far more ancient, perhaps possessing subtle, long-range correlations or patterns that were previously missed because they were expected to be stretched by expansion. New simulations modeled structure formation in a non-expanding cosmos, seeking to explain the observed distribution of galaxies solely through gravitational self-organization within a stable continuum. This led to new insights into the hierarchical formation of cosmic structures and the true role of gravity in shaping the grand tapestry of the universe, offering a clearer picture of its architecture, free from the influence of accelerating spatial stretching. The possibility of cosmic fatigue in light, while a crude descriptor for CFIT, was a misnomer to be corrected. Thorne emphasized that his theory was not about photons simply losing energy as they traversed space in a random way, like tired light theories of old, which would lead to blurred images of distant objects. Instead, he proposed a systematic quantum-level interaction with spacetime's intrinsic properties, causing a precise lengthening of wavelengths that mimicked expansion without blurring. This distinction was crucial. Blurring of distant objects was never observed, a key reason why older tired light theories were dismissed. CFIT, however, predicted no such blurring, as the interaction was a wavelength shift, not a scattering process. This addressed a significant historical objection and allowed CFIT to maintain coherence with all existing observations of cosmic image clarity, separating it definitively from discredited predecessors and establishing its unique position as a rigorous, testable, and robust theoretical contender for describing fundamental cosmic dynamics. The fundamental energy budget of the static universe became a new area of intense study. In the Big Bang model, the universe's energy density was dominated by dark energy, dark matter, and then baryonic matter. In a static universe without dark energy, and potentially with a re-evaluation of dark matter, the energy composition would be drastically different. What was the dominant form of energy in this static cosmos? Was the cosmic fabric itself a pervasive energy source? Did the zero-point energy of spacetime contribute significantly to the total energy density, perhaps even accounting for some of the previously mysterious dark components? New theoretical models explored how energy could be conserved in an eternal, recycling universe, and how the inherent vacuum energy might play a more active role in shaping cosmic phenomena than previously thought. This was a profound reevaluation of the universe's fundamental composition, bringing physicists closer to understanding the true nature of the energy that permeated and sustained all of reality, without the need for hypothetical unseen forms. The concept of quantum entanglement gained new relevance in the context of CFIT. Could the subtle interactions of photons with the cosmic fabric over vast distances be mediated by some form of non-local quantum connection? Some speculative theories propose that the very fabric of spacetime possessed an inherent entanglement, a universal interconnectedness that subtly influenced photon wavelengths as they traversed cosmic distances. This idea, while still highly theoretical, opened up exciting possibilities for understanding how quantum phenomena might scale to cosmological dimensions, bridging the gap between the incredibly small and the unimaginably large. If the universe itself was permeated by a fundamental quantum entanglement, it would offer a profound new layer of understanding to the fabric's properties and its interaction with light, revealing a universe far more integrated and quantum-driven than previously conceived, where non-local connections might be fundamental to cosmic dynamics. This was a true frontier of theoretical thought, venturing into the deepest realms of quantum reality. The legacy of Thorne's cosmic fabric interaction theory isn't just about replacing one cosmological model with another. It's about a fundamental shift in scientific methodology and philosophy. It demonstrated the crucial importance of challenging deeply held assumptions, even those supported by seemingly overwhelming evidence. It highlighted the power of reinterpreting observational data through entirely new theoretical lenses, rather than always trying to fit new data into old frameworks. This shift fostered an intellectual atmosphere of greater openness, inviting more daring and unconventional ideas into mainstream discourse. It was a victory for scientific humility and intellectual courage, reminding us that the universe is far stranger and more subtle than our most sophisticated models might suggest, and that true progress often comes from those who dare to question the very foundations of accepted truth. The universe, in its static, unchanging majesty, had delivered a profound lesson. Never stop questioning, never stop exploring, for the deepest truths often lie hidden in plain sight, waiting for the right mind to unlock their secrets. The confirmation of CFIT led to a surge in interdisciplinary research. Biologists, for instance, began to explore the implications of an eternal universe for abiogenesis, the origin of life itself. If the universe had always existed, then there was effectively infinite time for life to spontaneously emerge and evolve on countless planets across the cosmos. This drastically increased the statistical probability of life originating, perhaps even multiple times, in various forms, rather than being a singular, improbable event in a fleeting, nascent universe. Ecologists considered cosmic ecosystems, where life might repeatedly emerge, flourish, and become extinct over eons, creating an eternal ebb and flow of biological complexity throughout the cosmos. This provided a far grander canvas for the story of life, shifting the focus from a unique, rare occurrence to a potentially continuous and self-replicating cosmic phenomenon. It offered a profound answer to the question of, are we alone, by suggesting the universe was perpetually teeming with the potential for life, a timeless cradle for biological evolution on an unimaginable scale. The re-evaluation of cosmic evolution profoundly impacted theoretical astrophysics. Without a singular beginning, models of galaxy formation and large-scale structure had to account for processes occurring over an infinite history. How did the very first stars form in a potentially unending universe? Did they ever truly end? Or did their remnants perpetually cycle into new generations? New research focused on mechanisms for continuous reprocessing of cosmic gas and dust, ensuring that raw material for star formation remained abundant throughout eternity. This challenged traditional notions of stellar populations, suggesting that very old population 3 stars could still be forming today in isolated pockets, or that the oldest stars could be far, far older than previously imaginable. The universe, no longer constrained by a thermal Big Bang timeline, was now a grand, perpetual motion machine, efficiently recycling its matter and energy to maintain a timeless cycle of creation and recreation. The very concept of universe expanded beyond merely the observable cosmos. In an expanding universe, the edge of observations was constantly receding, defining the limits of what we could ever see. But in a static universe, there was no expanding edge. The observable universe was merely the region from which light had had time to reach us. Beyond that was more static universe, potentially infinite in extent, filled with countless more galaxies and structures that simply hadn't revealed themselves yet. This philosophical shift implied that our current observable universe was just an infinitesimal patch of a boundless, timeless reality, rather than the entirety of existence. It presented humanity with an even grander canvas for exploration, suggesting that the ultimate reality was far vaster and richer than previously conceived, an endless expanse of structure and possibility that continued beyond the limits of current perception, beckoning us to perpetually expand our horizons. The discovery of Thorne's cosmic fabric interaction theory revitalized the public's fascination with astronomy. Educational institutions reported a surge in enrollment for physics and astronomy courses, driven by a new generation eager to explore the secrets of the static universe. Amateur astronomers, once content to view receding galaxies, now sought to understand the subtle optical effects that mask the universe's true stillness. Citizen science projects aimed at analyzing vast astronomical datasets for new patterns supportive of CFIT flourished. The universe, no longer just a scientific concept, became a source of profound personal revelation and intellectual adventure for millions, fostering a widespread public engagement with the deepest questions of existence. This was a testament to the power of scientific discovery to inspire and unite humanity, proving that even the most complex ideas, when stripped of dogma, could ignite a universal curiosity and a shared journey towards a grander cosmic truth. One of the profound implications of a static, eternal universe was the potential for the eventual emergence of truly cosmic-scale intelligence. Unconstrained by a finite cosmic lifespan, life, if continuously occurring throughout the universe, could conceivably evolve into forms of consciousness that transcend planetary or even galactic boundaries. What would it mean for intelligence to have billions, even trillions of years to evolve? Could such entities eventually interact with the cosmic fabric itself, perhaps manipulating its properties, or even becoming one with the underlying structure of spacetime? This pushed the boundaries of theoretical science into the realm of speculative evolution, inspiring new lines of thinking about ultimate forms of existence. The universe, without a beginning or end, allowed for the gradual, inexorable unfolding of complexity and consciousness on truly unlimited scales, hinting at a future where intelligence might not just observe the cosmos, but profoundly interact with and even embody its eternal nature. The mathematical elegance of CFIT was a source of profound satisfaction for Thorne and his fellow theorists. While the Big Bang model often required additional parameters and cosmological constants to fit observations, CFIT, once its core mechanism was understood, offered a more parsimonious explanation. The entire suite of observed cosmic phenomena, redshift, CMB, elemental abundances, large-scale structures, and even the apparent acceleration, could be explained by fewer fundamental assumptions, relying more on the inherent properties of space and light interaction. This simplicity, this reduction in arbitrary parameters, was considered a hallmark of a powerful and potentially true scientific theory. It suggested that the universe, at its deepest level, was simpler and more unified than previously thought, governed by a few elegant principles rather than a complex web of disconnected phenomena. The universe, it turned out, was not expanded by a chaotic explosion, but exquisitely calibrated by an underlying, elegant and unchanging cosmic harmony. The scientific community recognized that while CFIT explained observed phenomena without the need for expansion, a complete understanding still required identifying the precise quantum mechanical mechanism of the cosmic fabric interaction. Was it a subtle modification to the photon's wave function, a continuous interaction with virtual particles, or something entirely new beyond the standard model of particle physics? Research focused on developing quantum gravity theories that could naturally incorporate such an interactive fabric, potentially bridging the chasm between general relativity and quantum mechanics. New particle accelerators were proposed, not just to smash particles, but to create extreme conditions that might allow for minute, observable interactions between light and the vacuum itself, mimicking the cosmic scale in a lab. This was the holy grail of fundamental physics, driven by the new cosmological understanding, promising to unlock the very secrets of existence at its most elementary level, leading towards a unified theory of all forces and particles, all within the timeless embrace of a static universe. The historical debate between the Big Bang and alternative models, particularly the steady-state theory, gained new relevance. The steady-state model, championed by Fred Hoyle, proposed a universe that, while expanding, was also continuously creating new matter to maintain a constant density over time, thus having no beginning or end. While ultimately disproven by the CMB discovery, its philosophical underpinning of an eternal universe resonated with CFIT. Historians of science revisited Hoyle's work, not to validate his expansion, but to acknowledge his foresight in advocating for a timeless cosmos. The new static universe model, while not identical to steady state, borrowed its premise of an eternal, unchanging system on the largest scales, but explained the expansion illusion differently. This re-engagement with past theories showcased how scientific knowledge progresses, not always linearly, but often by recycling and refining ideas from forgotten corners, proving that even seemingly wrong theories can contain hidden grains of future truth. The impact of CFIT on space exploration strategies was significant. If the universe was static, with no end in sight, then the long-term prospects for humanity's presence in the cosmos changed dramatically. Rather than a desperate race to escape an inevitably cold and empty universe, or a flight from a collapsing one, humanity could envision a future of long-term, sustainable expansion throughout a timeless galaxy and beyond. IO propulsion, generational starships, and self-replicating probes gained new urgency, driven by the prospect of colonizing a perpetually available, unchanging cosmic frontier. The goal shifted from mere survival to flourishing within an eternal cosmos, adapting to its rhythms and exploring its boundless depths without the pressure of an expiring cosmic clock. This broadened humanity's cosmic ambition, inviting us to become stewards of life within an eternal universe, rather than merely temporary visitors in a fleeting cosmic moment. The re-evaluation of cosmic element abundance became a more nuanced discussion within a static universe. While the Big Bang model offered a robust explanation for light-element ratios, a static universe compelled new theoretical work on how continuous creation and recycling of matter over infinite timescales could similarly account for observed abundances. Perhaps primordial nucleosynthesis occurred, but in a localized, cyclical manner within the cosmic fabric, rather than a single event. Or perhaps stellar processes, over a vastly extended cosmic history, slowly but surely built up the cosmic inventory of heavier elements, while light elements continually replenished through unseen processes or inherent properties of the cosmic fabric itself. This pushed the boundaries of nuclear astrophysics, demanding new models to describe element formation and evolution in a perpetually existing, self-sustaining cosmos, ensuring a continuous supply of fundamental building blocks without relying on a singular cosmic genesis event, thus ensuring endless possibilities for future chemical evolution. The concept of the multiverse, while still speculative, took on new forms in the static universe. Instead of an infinite number of inflating Big Bang bubble universes, perhaps the multiverse implied an infinite expanse within our own static universe, with regions possessing varying physical laws or different manifestations of the cosmic fabric. Or perhaps other universes existed as distinct, unchanging realities, eternally separated but governed by the same underlying cosmic fabric principles. This subtly shifted the focus from creation events of new universes to the inherent variations within an eternal, overarching cosmic reality. It offered a different flavor of cosmic multiplicity, one where existence was not a series of distinct cosmic births, but a boundless, continuous expanse of varied realities, a truly infinite spectrum of cosmic possibilities all existing simultaneously within a single, overarching static cosmos, forever defying a singular origin point and promising endless forms of existence to be understood. Thorne's work inspired a new generation of scientists to embrace radical empiricism, a methodological approach that prioritizes observational data above all else, even when it challenges established theories. This meant actively seeking out anomalies, contradictions, and subtle deviations from predicted outcomes, treating them not as nuisances, but as crucial clues to deeper physical realities. It encouraged cross-disciplinary collaboration, inviting experts from fields like quantum optics, material science, and computational physics to contribute their unique perspectives to cosmological problems. The universe, it seemed, was not always going to reveal its secrets in straightforward ways, and understanding its static nature required an open mind, an insatiable curiosity, and a willingness to constantly question the very foundations of scientific thought. This intellectual shift fostered a dynamic and self-correcting scientific culture, ensuring that future discoveries would arise from a rigorous, humble, and endlessly questioning engagement with the universe's most profound mysteries. The very concept of infinity gained a new, tangible meaning. In an expanding universe, infinity was a theoretical extrapolation of future expansion, or the hypothetical extent beyond the observable edge. In a static universe, infinity became a more immediate and present reality, not just a mathematical concept but a description of existence itself. The universe had always existed and would always exist. It might be spatially infinite, an endless expanse of galaxies and structures. This profound shift in understanding impacted philosophy, mathematics, and even spiritual thought, grappling with the tangible implications of true cosmic boundless. What does it mean for our lives, our choices, and our perceived purpose if our existence is but an infinitesimal flicker within an eternal infinite whole? This was a universe that continuously transcended human scale, demanding a new level of awe and intellectual humility, inviting us to contemplate the profound and ever-present nature of true, boundless eternity. The artistic and cultural impact of the static universe was immense. Science fiction writers embraced a new cosmic paradigm, crafting narratives of timeless civilizations, perpetual journeys through an unchanging cosmos, and encounters with ancient intelligences that had evolved over eons. Artists created breathtaking visualizations of the cosmic fabric, depicting its subtle interactions with light and its role in shaping reality. Musicians composed symphonies inspired by the eternal hum of the CMB, reimagined as the universe's inherent song. This widespread cultural engagement reflected humanity's innate desire to understand its place in the cosmos. And the new static universe offered a richer, more profound narrative than the previous, more finite Big Bang story. It spurred a renaissance of cosmic storytelling across all media, showing how scientific understanding profoundly shapes our collective imagination and our desire to connect with the grand, unchanging narrative of existence itself, providing a sense of comfort and endless wonder within a timeless reality. The search for the elusive cosmic texture became a new priority. If the cosmic fabric was truly an interacting medium, it might possess a subtle texture or grain on incredibly small scales, smaller than atoms. This texture could correspond to the fundamental quantum fluctuations of space-time. New theoretical models attempted to predict the precise nature of this texture, and experimental physicists began to design interferometers and quantum sensors with unprecedented sensitivity to try and detect it. Imagine trying to feel the grain of a seemingly smooth surface by using the most precise instruments imaginable. This frontier research aimed to directly probe the quantum nature of space-time, pushing the boundaries of our ability to measure and understand reality at its most fundamental level. The universe, it turned out, was not just static, it was also subtly textured. Its very foundation, a complex tapestry of energetic quantum interactions, waiting to be revealed by the most precise instruments ever conceived. The re-evaluation of gravitational lensing effects, where massive objects bend the path of light, became more intricate. While the phenomenon itself remained an astounding confirmation of general relativity, how lensing manifested in a static, interactive universe required careful reanalysis. Did light's interaction with the cosmic fabric subtly modify the lensing effect over vast distances? Could the accumulated interactions of light with the fabric alter the apparent positions or magnifications of distant lensed objects? New simulations integrated CFIT into gravitational lensing models, seeking to refine our understanding of mass distribution and space-time curvature in a non-expanding cosmos. This meticulous work aimed to resolve any potential discrepancies with observed lensing phenomena, ensuring that CFIT could consistently explain all cosmic observations, even the most complex ones, further solidifying its position as the accurate description of reality, elegantly explaining an even wider range of cosmic phenomena. The existence of very old stars, far older than the accepted age of the universe according to the Big Bang model, sometimes called cosmic Methuselahs or impossible stars, now found a natural home within the static universe. In an eternal cosmos, stars could indeed be trillions of years old, having formed and evolved over timescales far beyond the previous 13.8 billion year limit. Their existence was no longer an anomaly to be explained away by measurement uncertainties. It was direct evidence of a timeless universe. This not only resolved a long-standing puzzle, but also opened up fascinating new research into extreme stellar evolution models, exploring how stars could sustain themselves for such immense durations, or how their elemental composition might reflect an extremely long history of nucleosynthesis and recycling. The oldest stars, once an uncomfortable riddle, now became profound living fossils, whispering secrets of an eternal, unchanging cosmic past beyond any previous imagination, forever altering our understanding of stellar life cycles. The question of whether the cosmic fabric could eventually be mapped or directly imaged became a new grand endeavor for astronomers. If it possessed subtle fluctuations or density variations on large scales, could these variations leave an imprint on light that was detectable? Beyond just inferring its properties from redshift, could we directly visualize it? This imaginative concept pushed the boundaries of observational astronomy, proposing techniques that went beyond conventional light gathering. Perhaps through novel quantum interference experiments conducted across vast cosmic distances, or by detecting ultra-low frequency gravitational wave signatures that interacted uniquely with the fabric, a direct image of spacetime's intrinsic structure might one day be achieved. This was a long-term, ambitious vision, but the possibility of seeing the very fabric of reality, the medium through which all light travels and all events unfold, was a powerful motivator, promising the ultimate atlas of existence itself. The re-evaluation of cosmic expansion also had an impact on the search for exotic matter. In the Big Bang model, dark matter and dark energy were the primary forms of exotic matter. With CFIT, dark energy was eliminated. While dark matter still presented a puzzle, new avenues opened. Perhaps the cosmic fabric itself could have exotic properties, or be composed of yet-to-be-discovered particles that interacted with regular matter and gravity in unforeseen ways. Or perhaps there were other forms of unseen matter that behaved differently in a static universe than conventionally assumed, or that our current models for their detection were incomplete. This spurred an open-minded pursuit of alternative theories for cosmic mass and energy, moving beyond the standard dark matter candidates to explore a broader spectrum of possibilities. The universe, no longer constrained by the old paradigm, invited a more comprehensive and imaginative search for the true nature of its constituent components, promising new forms of matter and energy to be discovered, patiently waiting for their reveal. The influence of CFIT extended to inspiring new mathematical frameworks and geometries for describing the universe. While Euclidean and Riemannian geometries underpinned much of classical cosmology, theorists began to explore new, non-traditional geometries that could better describe a static, interactive spacetime. Could the cosmic fabric manifest as a higher dimensional space that subtly affected our perceived 3D reality, creating the illusion of expansion? Could fractal geometries or topologically unusual spaces offer more accurate descriptions of an infinitely large yet subtly structured universe? This pushed the boundaries of pure mathematics, seeking new tools to describe the complex, interactive nature of reality as revealed by CFIT. It demonstrated how profound scientific discoveries often necessitate equally profound advancements in the language of mathematics, providing new ways to conceptualize and quantify the universe's ultimate structure, moving beyond familiar forms to grasp a more profound, intricately beautiful cosmic order. The concept of the voids in the cosmic web, vast empty regions between galaxy filaments, also gained new attention. In the Big Bang model, these voids grow as the universe expands, pulling matter away from them. In a static universe, their existence and evolution demanded a different explanation. Were they simply regions of extremely low initial density that gravity continued to evacuate over eons? Or did the cosmic fabric itself possess subtle, localized properties that influenced the distribution of matter, perhaps even subtly repelling matter from certain regions? Researchers began to model void evolution in a non-expanding cosmos, examining how the interplay of gravity and the cosmic fabric might sculpt these immense cosmic deserts. This offered a more nuanced understanding of the universe's large-scale structure, suggesting that voids were not just passive gaps stretched by expansion, but dynamic, actively evolving regions shaped by the long-term, intricate dance of gravity and the inherent properties of space-time itself, unveiling their hidden role in cosmic structure. The age-old question of where did everything come from continued to challenge philosophers and scientists, even with the static universe model. While CFIT eliminated a singular Big Bang origin, it replaced it with the concept of an eternal, self-sustaining cosmos. But how did this eternity begin? Or had it always been? New philosophical treatises explored the nature of infinite regression and whether the question of a first cause was even applicable to a timeless universe. Religious scholars reinterpreted creation myths through the lens of a perpetually existing cosmos, finding new depths of meaning in cyclical narratives. This ongoing quest for ultimate origins, though reframed, continued to drive human inquiry, demonstrating that science, no matter how profound its discoveries, will always lead to deeper, more existential questions about reality itself. The universe, in its timeless existence, presented humanity with an ultimate, unending philosophical frontier, forever beckoning us to ponder its deepest, most fundamental mysteries. The implications for the concept of fundamental physical constants, like the speed of light or Planck's constant, were also re-examined within the static universe. If the cosmic fabric was an active, interactive medium, could it subtly influence the perceived values of these constants over vast cosmic scales or over truly immense timescales? While local measurements would remain consistent, perhaps precise observations from the most distant reaches of the universe might reveal minute, unpredicted variations. This spurred new experimental proposals to remeasure constants with extreme precision at various distances or epochs, seeking minute deviations that could provide further clues to the cosmic fabric's nature. This was a bold challenge to one of the most fundamental tenets of physics, the invariance of natural constants, opening up a thrilling frontier where the very laws of physics might prove to be subtly dynamic, not through expansion, but through their inherent interaction with the omnipresent, unchanging fabric itself. The search for cosmic echoes took on new meaning. In the Big Bang model, the CMB was the most prominent echo. In a static universe, were there other, previously unrecognized echoes or background radiations, perhaps from a constantly recycling cosmos, or from the inherent energetic processes within the cosmic fabric? Scientists looked for new forms of background energy or faint, pervasive signals that might be too subtle to detect with previous instruments. This could include a background of neutrinos or ultra-high-energy cosmic rays cycling through the universe over immense timescales, or even faint gravitational wave backgrounds from a perpetually active cosmic fabric. These new echoes would provide further insights into the static universe's processes, revealing its hidden energy dynamics, its perpetual recycling mechanisms, and the subtle, unchanging hum of its overall structure, further differentiating it from the Big Bang's single primordial afterglow. The concept of redshift quantization, a controversial idea suggesting that redshifts occur in discrete steps rather than a continuous spectrum, was also revisited. While largely dismissed in the expanding universe, some theorists wondered if such a phenomenon, if it existed, could be explained by CFIT. Perhaps the interaction of light with the cosmic fabric occurred in discrete quantum steps over vast distances, leading to a quantized redshift. This was highly speculative, but the new freedom offered by CFIT allowed for exploration of such radical ideas. It challenged cosmologists to consider whether the universe's ultimate structure was fundamentally granular on cosmic scales, not just on subatomic ones, and whether the interaction of light with this underlying grain caused the observed redshift in quantized increments. This pushed the boundaries of quantum cosmology, exploring the deepest implications of a digital or quantized reality on the largest cosmic scales, further deepening the mystery of light's ultimate interaction with the fabric of space. The implications of a static universe for black holes were particularly fascinating. Without a Big Bang singularity, how might black holes form and evolve over eternal timescales? Some theories proposed that the cosmic fabric might itself limit the maximum density of matter, preventing true singularities altogether. Instead, black holes might be fuzzballs, or regions of extreme but finite density, where the cosmic fabric itself becomes incredibly warped and active, perhaps even facilitating the gradual re-emission of matter back into the universe over eons. This offered a resolution to the information paradox, the problem of what happens to information swallowed by a black hole, by suggesting that information is never truly lost, but perhaps subtly encoded in the cosmic fabric itself. This radically reinterpreted the most extreme objects in the universe, integrating them into the perpetual recycling and unchanging nature of a static cosmos, showing that even these cosmic behemoths obeyed the fundamental laws of an eternally self-sustaining reality. The search for cosmic memory became a new topic of highly speculative research. If the universe had always existed, always recycling itself, could there be a form of cosmic memory embedded within the fabric itself, perhaps a residual imprint of past events? This was a highly abstract concept, bordering on metaphysics, but it explored ideas of information conservation and the universe as a vast, enduring computational system. Some theories proposed that the quantum fluctuations of the cosmic fabric might retain subtle informational imprints from billions of years of cosmic evolution. While purely theoretical, it highlighted the profound shift in perspective brought about by Sci-Fi. The universe was no longer a temporary stage but an eternal entity, a boundless repository of time and information, continuously interacting with and subtly recording the history of its perpetual existence. What secrets might such a cosmic memory hold, if it could ever be accessed or understood? The precise measurement of the cosmological dark flow, a mysterious coherent motion of galaxy clusters that appears to be independent of the universe's expansion, gained renewed relevance. In an expanding universe, the dark flow was an anomaly, suggesting an unseen, large-scale gravitational pull beyond the observable horizon. In a static universe, such large-scale coherent motions could indicate different phenomena. Perhaps they were evidence of vast, ultra-ancient structures of normal or modified matter in the truly distant, unobservable cosmos, exerting a gravitational influence. Or perhaps they were subtle, long-range currents within the cosmic fabric itself, causing a collective drift of matter. This reinvestigation offered new avenues for understanding grand cosmic dynamics, suggesting that the universe's large-scale motions were not relics of an early inflationary push, but rather manifestations of long-term gravitational interactions or subtle flows within the fabric of a timeless, unchanging cosmos. The search for cosmic strings or other topological defects in spacetime, remnants from the early universe in some Big Bang models, found new context in a static universe. While Sci-Fi removed the impetus for their formation from an explosive beginning, some theorists pondered if the cosmic fabric itself could inherently possess such defects, or stable, long-lived structures. Could these cosmic strings be manifestations of the fabric's fundamental properties, rather than relics of a primordial phase transition? This prompted new mathematical explorations of the fabric's topology and internal structure, searching for stable, non-expanding configurations that could explain such phenomena. It suggested that if such exotic structures truly existed, they might be inherent features of an eternal, self-consistent cosmos, rather than transient imprints of a violent birth, further cementing the timeless nature of the universe's most fundamental constituents. The concept of cosmic boundaries, or the universe's ultimate shape, was redefined. In an expanding universe, the shape often referred to its curvature flat, open, or closed, and its potential for recollapse or infinite expansion. In a static universe, the curvature could still exist, defining its overall geometry, but without the dynamic implications of expansion. The questions shifted. Was the static universe spatially finite but unbounded, like the surface of a sphere? Or was it truly infinite in extent, a boundless expanse of matter and energy existing perpetually? New observational tests were devised to precisely measure the universe's curvature, searching for subtle geometric distortions in the distribution of distant galaxies that would reveal its ultimate shape, stripped of the dynamic implications of expansion. This refined our understanding of the universe's grand architecture, revealing its unchanging, eternal form, a timeless canvas upon which all cosmic events unfolded. The philosophical implications for human self-awareness and consciousness within an eternal, static cosmos were also profound. If the universe had no beginning or end, and consciousness was a continuously emerging phenomenon, what was its ultimate destiny? Could consciousness, over eons, transcend its biological origins and become a fundamental aspect of the cosmic fabric itself? This highly speculative area of cosmic consciousness explored theories where information, thought, and awareness could be properties inherent to the universe's deeper structure, or that advanced intelligences could eventually merge with the cosmic fabric. becoming immortal, omnipresent entities. While far from scientific consensus, these discussions illustrated how Sci-Fi inspired truly visionary thinking about the ultimate purpose and fate of intelligence within a timeless reality, blurring the lines between life, consciousness, and the very fabric of existence itself, offering a grander, more enduring narrative for the destiny of thought. The challenge of observing the most distant galaxies, those at the highest redshifts, took on a new dimension. In the Big Bang model, these were the very first galaxies formed in the young universe, offering a glimpse into cosmic dawn. In a static universe, however, their high redshift merely indicated extreme distance and the cumulative effects of light fabric interaction. While still incredibly old, their observed properties like smaller size or lower metallicity might be due to intrinsic evolutionary factors occurring over vast timescales within a static cosmos, rather than their being, quote, primordial. New observational programs focused on these ultra-distant galaxies, seeking subtle structural or chemical signatures that would distinguish between a young galaxy in an expanding universe and an extremely distant galaxy in a static one, disentangling the effects of age from the effects of distance and light's journey, revealing their true nature within a timeless reality. Theoretical physicists began to develop new models for the very early moments of a static universe, replacing the Big Bang with concepts like eternal genesis or continuous creation. These models proposed that matter and energy were constantly emerging from the cosmic fabric itself, or from subtle quantum fluctuations of the vacuum, at a rate that maintained universal equilibrium. This was not a singular explosive event, but a perpetual self-sustaining process happening everywhere, all the time. Such models had to carefully balance creation with destruction and recycling to maintain a constant density and temperature, consistent with observations like the CMB. It was an ambitious endeavor, pushing the limits of theoretical physics to describe a universe that had no beginning, but was perpetually born anew from its own inherent properties, offering a profound and elegant alternative to the cataclysmic Big Bang, a universe in endless, self-generated renewal. The hunt for gravitational waves as a probe of the cosmic fabric intensified. While gravitational wave observatories like LIGO and Virgo had confirmed Einstein's predictions, new theories suggested that the cosmic fabric itself might subtly influence the propagation of these waves over vast distances. Could the fabric introduce minute distortions or attenuations in gravitational wave signals that were distinct from those caused by regular matter and energy? Future gravitational wave detectors with even greater sensitivity and longer baselines were proposed to search for these subtle imprints, hoping to directly detect the interaction of gravity with the fabric of space-time itself. This would provide an entirely new window into the universe's structure, allowing scientists to listen to the whispers of the cosmic fabric, confirming its existence and its active role in shaping all cosmic phenomena, from the largest structures to the subtle ripples of gravity, revealing its pervasive, unchanging influence. The concept of cosmic clocks that measure the rate of time's passage at different cosmic epochs was revisited. In an expanding universe, distant clocks would appear to run slower due to cosmological time dilation. In a static universe, such effects would need a different explanation. If the cosmic fabric subtly affected the propagation of light, could it also, in some way, affect the rate of physical processes over vast distances? This pushed the boundaries of relativistic effects, exploring how local time might be subtly influenced by the properties of the pervasive cosmic medium itself. New observational proposals aimed to meticulously measure the rates of distant cosmic events, like supernova light curves or galaxy rotation, to discern if the perceived slowing of time was purely an observational effect of light traveling through a static, interactive medium, or if some deeper temporal property was at play, forever challenging our understanding of time's universal march. The artistic and philosophical implications for the meaning of change in a static universe were profound. If the universe, on its grandest scale, was unchanging and eternal, what did that imply for motion, evolution, and the very concept of historical progression? This led to deep discussions on the nature of process versus stasis, and how local change could occur within a globally unchanging system. Artists explored themes of perpetual motion, cyclical rebirth, and the illusion of progress. Philosophers debated whether true progress exists in an eternal cosmos, or if all movement is part of a grand, timeless dance. This challenged human intuition, accustomed to linear causality and a finite lifespan, forcing a reevaluation of how meaning and purpose could be found in a universe that simply is, forever existing and evolving within its own inherent, enduring rhythm. The search for primordial black holes. Hypothetical black holes formed in the early universe gained new context in a static cosmos. Without a Big Bang providing extreme densities for their formation, how would they arise? Could they be continually forming from overdensities in the cosmic fabric or through extreme gravitational collapse in a timeless setting? New theoretical models explored alternative formation mechanisms, and new observational searches focused on detecting their signatures, not as relics of a violent birth, but as persistent features of a perpetually evolving static universe. This spurred a renewed interest in these elusive objects, no longer confined to a single epoch, but potentially forming and existing throughout cosmic history, offering new insights into the enduring processes of extreme gravitational collapse and the self-organizing properties of a timeless cosmos. The very concept of thermal death for the universe, a chilling Big Bang prediction of an infinitely expanded, cold, and empty future, was now completely discarded. In a static universe where the cosmic fabric maintained its equilibrium and matter and energy perpetually cycled, such an end was impossible. The universe, in its timeless existence, would always maintain a fundamental energy density, constantly renewing its stars and galaxies. This offered a profoundly optimistic outlook on the universe's ultimate destiny. It meant that life, consciousness, and complexity would never truly face an absolute end due to cosmic decay, but would always have the potential to emerge and evolve within the boundless, self-sustaining embrace of an eternal reality. The universe, it turned out, was not dying but forever living, a perpetual motion machine of existence, constantly recreating itself without any finite limits. The re-examination of galaxy morphology and evolution also changed significantly. In an expanding universe, galaxy shapes and sizes are thought to evolve over cosmic time due to mergers and accretion within the expanding metric. In a static universe, these processes still occurred, but over vastly longer, perhaps infinite timescales. This meant that the diversity of galaxy forms, from chaotic spirals to serene ellipticals, could be attributed more to intrinsic evolutionary paths operating over endless eons rather than being influenced by a singular burst of initial conditions. New simulations explored how galaxies could maintain their grand designs or transform over immense durations in a non-expanding medium. This offered a more detailed understanding of galactic dynamics, allowing for the formation of truly ancient, undisturbed structures and revealing a cosmic ballet where galaxies performed their timeless dance within a perpetually unchanging, boundless stage, a testament to enduring gravitational forces. The profound shift from an expanding to a static universe inspired a new golden age of cosmic inquiry. The sense of mystery, far from being diminished, was magnified by the realization that the universe was so much more subtle and complex than previously imagined. Every observation, every theoretical concept, was now viewed through a refreshed lens, revealing hidden layers of meaning. Scientists, artists, and philosophers alike were captivated by the idea of an eternal cosmos, its secrets unfolding not in a linear progression, but in an endless exploration of its inherent, unchanging depths. It was a testament to humanity's tireless quest for knowledge, proving that even as we unravel one grand mystery, the universe unveils new, even more profound enigmas, inviting us to delve ever deeper into its timeless, boundless, and infinitely fascinating nature, forever pushing the boundaries of human understanding. The universe, in its eternal embrace, beckoned us to join its endless, unchanging dance of discovery. The implications for the concept of empty space itself were perhaps the most radical. For centuries, philosophers and physicists debated whether space was a thing or merely the absence of things. Newtonian physics treated it as a passive container. Einstein's general relativity merged it with time into an active, malleable spacetime. But Thorne's cosmic fabric interaction theory went further. Space was not just malleable, it was a subtle, constantly interacting medium, bustling with quantum fluctuations, an inherent energy field that actively influenced light. It was the universe's pervasive, unchanging blood, silently shaping all observations. This elevation of empty space from a backdrop to a primary player fundamentally altered our understanding of reality, suggesting that the most seemingly mundane aspect of existence, the void between stars, was anything but empty. It was alive, vibrant, and incredibly influential, the true foundation upon which the timeless cosmos eternally manifested, forever challenging our intuitive notions of emptiness. The recalibration of cosmic distances had profound effects on stellar luminosity. If the observed dimming of distant objects was due to light's interaction with the cosmic fabric rather than geometric expansion, then the actual intrinsic brightness of distant large stars and supernovae had to be reevaluated. This provided a more accurate assessment of stellar evolution, as the intrinsic luminosities could now be determined with higher precision, unshackled from the expansion assumption. Astronomers could more accurately deduce the ages, masses, and compositions of distant star systems, leading to a richer understanding of how stars formed and evolved across the static universe's timeless expanse. The universe's stars, once distorted by the illusion of expansion, now shone with their true, unadulterated brilliance, revealing a more precise tapestry of stellar life and death throughout cosmic history, without the confounding effects of a disappearing horizon. The search for cosmic attractors, or great walls, immense, coherent superstructures of galaxies that seem to stretch across billions of light-years, also found new meaning. In a static universe, these structures could be truly ancient, having formed and grown over eons through gravitational self-organization and the subtle influence of the cosmic fabric. They were not merely statistical flukes of an expanding universe, but indelible features of a timeless, unchanging cosmic architecture. New simulations modeled their formation and stability in a non-expanding cosmos, seeking to understand the gravitational dynamics that could lead to such immense, enduring structures. This offered a more profound understanding of the universe's largest-scale organization, revealing a cosmic architecture that was far more stable, enduring, and intricately sculpted than previously thought, a testament to the timeless interplay of gravity and the pervasive, unchanging cosmic fabric, perpetually shaping the grand designs of the cosmos. The philosophical concept of eternal recurrence gained a powerful new scientific underpinning. If the universe had no beginning or end, and matter and energy perpetually cycled, it opened up the possibility, however remote, that identical cosmic configurations, or even identical lives, could recur over truly infinite timescales. While not a direct prediction of CFIT, the removal of a finite cosmic beginning and end made such philosophical concepts less of a purely abstract idea and more plausible within the realm of infinite temporal existence. This led to new interdisciplinary discussions, blending physics with philosophy, exploring the profound implications for free will, destiny, and the very meaning of personal existence in a universe where everything might, eventually, repeat. The static universe offered a grand stage for contemplating such profound existential questions, challenging humanity to grapple with the dizzying implications of a truly boundless and ever-repeating cosmic narrative. The cosmological redshifting of events, such as supernovae light curves, also underwent reinterpretation. In an expanding universe, the light from distant supernovae would appear stretched in time, meaning their explosion and fade-out would seem to take longer from our perspective. This time dilation was considered another strong proof of expansion. However, in a static universe, Thorne proposed that this perceived time dilation was another artifact of light's interaction with the cosmic fabric. The same mechanism that redshifted the light could also, over vast distances, subtly alter the perceived rate of temporal events. This complex interaction would create the illusion of time dilation, elegantly explaining the observed phenomenon without invoking spatial expansion. It was a testament to the comprehensive power of CFIT, able to unify various observations under a single, elegant mechanism, fundamentally rescribing the very rhythm of cosmic time, decoupling temporal perception from spatial dynamics. The search for cosmic backgrounds beyond the CMB gained new momentum. If the universe were truly eternal, it might possess a subtle, persistent background of other particles or energies that continuously permeated space, arising from its ongoing processes. This could include a faint, uniform background of neutrinos from countless stellar deaths over eons, or a diffuse glow of X-rays from the intergalactic medium, or even a background of ultra-high-energy cosmic rays cycling indefinitely. While distinct from the CMB, these backgrounds would collectively represent the inherent energetic hum of a perpetually existing universe, offering valuable clues to its material composition and ongoing processes. Detecting and characterizing these subtle, omnipresent backgrounds would provide further empirical validation for the static universe model, enriching our understanding of its energy budget and its timeless, self-sustaining nature, revealing further layers of its ongoing, quiet activity. The very concept of absolute zero was re-examined. In an infinitely expanding universe, the expectation was that it would eventually cool down to absolute zero, leading to a heat death. In a static, eternal universe, where energy and matter perpetually cycled, the thermal equilibrium might be maintained indefinitely. This implied that the universe, as a whole, might never truly reach absolute zero, always possessing some inherent background temperature or energy from its ongoing processes. New theoretical models explored mechanisms for maintaining thermal balance in a static cosmos, challenging the conventional view of increasing entropy as an inexorable cosmic fate. This offered a more comforting vision of the universe's long-term future, suggesting that it would always remain a dynamic, energetic place, capable of sustaining life and complex processes indefinitely, never succumbing to the ultimate chill of thermal death, perpetually maintaining its fundamental vitality. The implications for the origin of life beyond Earth were significantly broadened. If the universe was static and eternal, then the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of observed evidence, gained new angles. Perhaps life was indeed ubiquitous but arose and perished on timescales far exceeding our observation windows. Or civilizations became so advanced, they transcended their physical forms, making them undetectable. The sheer abundance of time allowed for an unimaginable diversity of life forms and evolutionary paths, making our single earthbound experience a mere snapshot in an eternal cosmic biological tapestry. This fostered a more expansive view of astrobiology, encouraging the search for not just simple life, but incredibly ancient, complex, and potentially vastly different forms of intelligence that might have emerged over billions of years in a timeless cosmos, challenging our anthropocentric assumptions about intelligence. The reevaluation of cosmic timescales led to a new understanding of astronomical fossils. Objects like globular clusters, thought to contain the oldest stars in the Big Bang model, now became even more intriguing. If the universe was timeless, what was their absolute age? Could some be inconceivably ancient, relics from an infinitely distant past? New methods were developed to estimate their true ages, divorced from the limited cosmic timeline of the Big Bang, revealing stellar populations potentially trillions of years old. This allowed astronomers to probe truly primordial conditions, examining the earliest phases of star formation in a truly ancient universe. These cosmic fossils, once merely benchmarks for a limited cosmic age, now revealed profound secrets of enduring stellar processes and the timeless evolution of galactic structures, becoming invaluable windows into an unimaginably deep cosmic history that stretched backward infinitely in time. The very concept of causality in an eternal, static universe gained new philosophical and physical dimensions. In a linear, finite universe, cause and effect typically follow a straightforward temporal progression. But if the universe has no beginning or end, and processes cycle perpetually, did that imply a form of cosmic self-causation, or loops that defied simple linear reasoning? This was a highly abstract and speculative area, but it challenged physicists and philosophers to explore complex, non-linear models of causation. It questioned whether certain cosmic phenomena were truly independent events or part of an inherent, self-sustaining cosmic dance, where everything was both cause and effect within a timeless continuum. The static universe, in its perpetual state of being, forced a re-evaluation of the most fundamental principles guiding our understanding of time, action, and reaction, pushing us to comprehend a cosmic order far more integrated and complex than previously conceived. The implications for cosmic weather, phenomena like solar flares, gamma-ray bursts, and supernova outbursts, were also re-evaluated. While these events are inherently transient and local, their frequency and distribution across an eternal universe gained new context. Was there a steady-state rate of such events, maintained over eons by continuous stellar processes? How would their cumulative energy impact the cosmic fabric over vast timescales? New statistical models were developed to predict the long-term patterns of cosmic transients in a static universe, divorced from the evolving density of an expanding cosmos. This led to a more refined understanding of the universe's dynamic activity within its overarching stillness, revealing how even the most violent cosmic events contributed to the perpetual energy balance of an eternal, self-sustaining reality, constantly recycling and transforming its constituents without a beginning or end. The very concept of life obtained a grander definition within a static, eternal universe. If consciousness and complexity were endlessly emerging, existing over cosmic timescales, then the definition of life expanded beyond biological, carbon-based forms. Could life exist as plasma beings, or as intricate patterns of energy within the cosmic fabric, or as information encoded in spacetime itself, sustained over billions of years? This sparked imaginative discussions, bridging exobiology with theoretical physics, exploring the conditions for non-traditional forms of life and intelligence in a timeless cosmos. It pushed beyond anthropocentric biases, forcing humanity to consider a universe teeming with countless, diverse forms of existence, some perhaps incomprehensibly ancient, others entirely alien to our current classifications, all part of an eternal, self-sustaining cosmic tapestry, demonstrating the boundless possibilities for existence within an unchanging reality. The re-examination of galaxy clusters, the largest gravitationally bound structures in the universe, took on new significance. In an expanding universe, their growth is limited by the acceleration of space pulling them apart. In a static universe, these massive structures were free to grow and consolidate over potentially infinite timescales unhindered by expansion. This meant that truly enormous, ancient galaxy clusters could exist, denser and more integrated than previously thought possible, potentially revealing new insights into large-scale gravitational dynamics. New observational efforts focused on searching for these, quote, cosmic behemoths, clusters so vast and old they would challenge Big Bang predictions, providing further evidence for a static, timeless cosmos. Their discovery would profoundly refine our understanding of the universe's enduring gravitational organization, revealing a cosmic architecture that was far more stable, massive, and truly majestic than previously conceived, testament to immense, unseen forces. The realization that our universe never expanded fundamentally altered the narrative of humanity's journey and our place within existence. We are no longer fleeting inhabitants of a cosmic flash, but part of an eternal, grand design. This inspired a new sense of cosmic responsibility and purpose, encouraging humanity to become perpetual explorers and guardians of life within a timeless cosmos. The universe, in its new, unchanging revelation, offered a profound sense of stability and belonging, replacing existential dread with unending wonder. It challenged us to think beyond our limited lifespan, to consider our impact on an eternal timescale, and to find meaning not in beginnings or ends, but in the continuous, unfolding process of existence itself. This was the ultimate payoff, a universe that was not expanding away from us, but inviting us to forever dwell within its infinite, unchanging embrace, beckoning us to understand its deeper secrets, perpetually. The challenge of accurately measuring the universe's ultimate age, now understood as infinite, also spurred new methods. While dating stars and galaxies remained important for understanding their relative ages, the focus shifted from a universal cosmic clock to understanding continuous processes of birth, death, and recycling over eons. Scientists looked for evidence of truly ancient, stable structures that had persisted for unimaginable durations, providing insights into the mechanisms of cosmic stability. This meant re-evaluating geological and planetary timescales as well, considering how they might fit into an infinite cosmic history. How could planetary systems form, persist, and potentially host life for truly vast stretches of time? The concept of an absolute age for the universe became a testament to its timelessness, a profound indicator of its eternal existence rather than a countdown from a singular beginning, perpetually challenging our human-centric notions of duration and cosmic chronology. The scientific exploration of the universe gained a new sense of urgency and wonder. Instead of racing against an expanding frontier or an accelerating demise, Humanity was now driven by the boundless, eternal nature of the cosmos. Every new discovery, every deeper understanding of the cosmic fabric, revealed more of a universe that had always existed and would always exist, full of endless secrets waiting to be unearthed. This was curiosity born not of fear, but of profound fascination, an insatiable desire to understand the endless complexities of a timeless reality. Scientists embarked on voyages of discovery, driven by the realization that the universe, in its stillness, was infinitely rich and perpetually offering new layers of understanding, a true boundless realm begging for endless exploration. The universe, once a fleeting moment, became the ultimate eternal adventure, inviting humanity to be its perpetual explorer. The philosophical implications of a timeless universe for human purpose and meaning were also extensively debated. If there was no cosmic goal or destination defined by a beginning and end, what then was the purpose of existence? Many found profound comfort and meaning in the idea of being part of an eternal, self-sustaining whole, finding purpose in continuous learning, stewardship, and the perpetual unfolding of consciousness. It shifted the locus of meaning from predetermined cosmic fates to the inherent value of present existence and the endless possibilities for creation and connection within an infinite duration. The universe, in its profound stillness, invited humanity to embrace a new form of cosmic optimism, finding purpose not in an ultimate conclusion, but in the unending journey of discovery, the perpetual dance of life, and the timeless mystery of existence itself. The re-evaluation of cosmic background radiation sources beyond the CMB continued to be a vibrant research area. If the universe truly was static and eternal, then it suggested a rich tapestry of background energies stemming from its continuous processes. These might include a gravitational wave background from countless black hole mergers over eons, or a cosmic ray background from perpetual supernovae. Researchers began to design new, highly sensitive detectors to precisely measure these incredibly faint, pervasive energies, hoping to map the different thermal and radiative components of the static universe's unchanging hum. This intricate mapping would provide unprecedented detail about the universe's ongoing dynamics, revealing its sustained activity without relying on a fiery, singular origin event, showing that even in its stillness, the cosmos was a vibrant, continuously active realm. The profound conceptual shift from an expanding to a static universe left humanity with a renewed sense of awe and a deeper appreciation for the universe's enduring mystery. It was a universe that constantly challenged our assumptions, demonstrating that even the most well-established theories could be overturned by persistent observation and radical thought. The cosmos in its newfound stillness was not less dynamic but differently dynamic, not less mysterious, but infinitely more so. This intellectual triumph reinforced the core values of scientific inquiry: curiosity, skepticism, humility, and the relentless pursuit of truth above all else. The universe, far from being just a subject of study, became a profound teacher, guiding humanity towards a more nuanced, open, and ultimately more wondrous understanding of reality, perpetually unveiling its secrets to those courageous enough to question the very foundations of accepted knowledge, forever expanding our minds, if not its own physical boundaries. Thus, the story of the universe was rewritten. No longer a fleeting phenomenon born from a fiery explosion, but an eternal, self-sustaining reality, its apparent expansion revealed as a grand illusion, a subtle interplay of light and the ubiquitous cosmic fabric. This was the universe unveiled, not in its final form, but in a new beginning of understanding. The journey was long, born from the quiet inquiry of brilliant minds, challenged by skepticism, and ultimately validated by overwhelming empirical evidence. It was a testament to the enduring power of scientific method, to question, to observe, to analyze, and to courageously follow where the data leads. This new cosmic narrative redefined humanity's place, inviting us to be eternal inhabitants and explorers of a boundless, timeless cosmos, perpetually revealing its secrets. The profound shift to a static universe inspired a re-evaluation of the concept of dimensions. If the cosmic fabric was a pervasive, interactive entity, did it imply the existence of hidden extra dimensions, perhaps curled up or subtly influencing our perceived three spatial dimensions and one time dimension? Some theorists proposed that the interaction of light with the fabric was a manifestation of photons subtly navigating through these higher dimensions, causing their wavelength to stretch. This opened up thrilling new avenues for theoretical physics, pushing the boundaries of our understanding of space-time itself. Were we merely observing a projection of a higher dimensional reality, and the illusion of expansion was a consequence of these unseen dimensions? It was a highly speculative but incredibly exciting area, suggesting that the universe held far more spatial complexity than previously assumed, beckoning us to explore the hidden realms of reality and their profound influence on our perceived existence within this timeless cosmos. The search for cosmic background noise beyond the CMB and gravitational waves gained prominence. If the universe had always existed, always recycling itself, it implied a perpetual generation of energy and particles. Could there be a background of very low-energy photons, or a faint, pervasive hum of neutrinos and antineutrinos, originating from the continuous, ancient processes of stellar nucleosynthesis and decay throughout eternity? This would not be a mere leftover, but an active, integral part of the universe's ongoing energy budget. New ultra-sensitive detectors were proposed, buried deep underground or deployed in space, to search for these elusive, omnipresent particles, hoping to map the subtle, unchanging energetic currents that traverse the static cosmos. Detecting such a background would provide further empirical validation for an eternal, self-sustaining universe, offering unprecedented insights into its pervasive, timeless, and perpetually active nature. The philosophical implications for human perception of scale were immense. Our minds are naturally equipped to comprehend a finite, human-scale existence, but a universe that has always existed and is spatially boundless forces a profound cognitive shift. How do we truly internalize the concept of infinite time and infinite space? This prompted new collaborations between cosmologists, neuroscientists, and cognitive psychologists, exploring the limits of human comprehension when faced with true cosmic infinity. It underscored the limitations of our intuitive understanding and the power of scientific models to transcend these limitations, enabling us to conceive of realities far grander and more alien than our everyday experience. The static universe, in its immense and unchanging nature, served as a profound intellectual and philosophical challenge, pushing humanity to expand the very boundaries of its imagination and perception, constantly striving to grasp the boundless depths of existence itself. The concept of cosmic dark matter also gained a new interpretation. While the Big Bang invoked it as collisionless particles formed in the early universe, in a static universe, its properties and origins might be different. Could dark matter be a specific, localized manifestation of the cosmic fabric itself, or a consequence of its interaction with visible matter? Some theoretical models explored how the very texture or properties of the cosmic fabric could mimic the gravitational effects attributed to dark matter, without needing additional particles. This offered a more unified explanation, integrating the dark matter puzzle into the comprehensive framework of Sci-Fi, suggesting that the universe's dark components were not external additions, but rather inherent properties or subtle manifestations of the pervasive, unchanging cosmic fabric itself. This promised to elegantly solve one of cosmology's greatest mysteries, further streamlining the universe's inventory. The ethical and societal implications of an eternal universe began to be debated. If humanity possessed an effectively infinite future within a boundless cosmos, did that impose new responsibilities for long-term stewardship of life, resources, and knowledge? What did it mean for overpopulation, resource depletion, or interspecies relations if existence was not limited by a cosmic clock? This spurred discussions on sustainable space colonization, the preservation of biodiversity across cosmic scales, and the long-term ethical evolution of intelligent life. The static universe provided a grand, enduring canvas for humanity's moral and societal evolution, challenging us to consider our actions not just in terms of generations, but in the context of eons of perpetual existence. It demanded a new form of cosmic wisdom, guiding humanity to embrace its role as a permanent, responsible inhabitant of a timeless and infinitely valuable cosmos. The potential for cosmic archaeology took on new dimensions. If the universe was timeless, then there could be incredibly ancient civilizations, or even pre-life structures, dating back far beyond what was previously conceivable. Scientists began to search for extremely subtle ancient technosignatures or megastructures, not just radio signals, but gravitational ripples from ancient cosmic engines, or anomalous energy signatures from long-dead cosmic civilizations. This was a search for true cosmic relics, not from a violent birth, but from an unimaginably long continuous history of existence. It broadened humanity's understanding of cosmic history, inviting us to look for evidence of life and intelligence that had thrived and evolved over eons, leaving their lasting imprint on the boundless, unchanging canvas of a timeless universe, forever changing our perception of cosmic history. The re-evaluation of the cold spots and hot spots in the cosmic microwave background also gained new interpretation. In the Big Bang, these subtle temperature fluctuations were the seeds from which all large-scale structures grew, imprinted during the very early universe. In a static universe, these fluctuations could be explained differently. Perhaps they were natural products of the cosmic fabric itself, subtle, inherent density fluctuations that slowly coalesced into galaxies over eons. Or, perhaps, they reflected underlying variations in the intrinsic properties of the cosmic fabric across vast distances, rather than primordial temperature differences. This opened up new mathematical models for structure formation, divorced from a singular inflationary origin and rooted firmly in the timeless interplay of gravity and the pervasive, unchanging cosmic fabric, revealing the subtle cosmic architecture of an eternal, self-organizing universe. The universe never expanded. This fundamental truth, once whispered by a few radical minds, now echoed across every observatory, every laboratory, every classroom on Earth and beyond. The scientific consensus had shifted, irrevocably. The cosmos, in its eternal stillness, had revealed its true face, a face of timeless grandeur, subtle dynamics, and boundless mystery. The illusion of expansion, so compelling for a century, had dissolved under the weight of new evidence and bold reinterpretation, replaced by a universe far more profound and elegantly self-sufficient. This was the ultimate payoff, the clarity of a static cosmos, where light's journey imparted its own unique, deceptive fingerprint, and the universe truly was an unchanging, endless tapestry, constantly inspiring new questions, new discoveries, and an unquenchable thirst for deeper understanding, forever challenging humanity to broaden its vision. The final legacy of Thorne's cosmic fabric interaction theory was not just a scientific model, but a revolution in human thought. It offered a profound answer to the most ancient questions: where do we come from, and where are we going? The answer: we have always been, and we will always be, part of an eternal, boundless cosmos. This sense of timeless continuity, of being deeply embedded within an unchanging, self-sustaining reality, changed humanity's relationship with time, destiny, and its own place in the grand tapestry of existence. The universe, in its revealed stillness, became a source of endless philosophical debate, artistic inspiration, and scientific wonder, perpetually inviting us to explore its depths with renewed awe and a greater understanding of our enduring connection to its silent, eternal rhythm. The universe, in its ultimate stillness, became a silent symphony of perpetual existence, beckoning us to listen ever closer. And so, the grand cosmic illusion was finally shattered. The universe, in its breathtaking and profound truth, never expanded. It simply, eternally is. It is a vast, unchanging stage upon which light performs its intricate dance with the very fabric of space, creating the illusion of cosmic recession. This revelation transformed humanity's understanding of its home, replacing a fleeting epoch with an eternal continuum, a cataclysmic birth with a timeless existence, and an uncertain end with perpetual renewal. This is the universe as it truly is, boundless, unchanging, and infinitely mysterious, forever inviting those who dare to look beyond the obvious to unlock its deepest, most enduring secrets. The journey of discovery continues, not towards an expanding horizon, but inward, into the boundless depths of a static, stunning, and truly eternal cosmos. The universe, forever still, forever beckons,